method is and the theory behind it. For those of you who are maybe less familiar with the technique, and for the second half of the session, I'll be giving a coding demonstration on the ReggeWheeler package with a focus on the MST method, where you'll be able to work on some problems and practice using the code. So you can download that notebook from the website now or later, whatever you like. I won't be demonstrating the MST method, Teukolsky package. It's pretty much exactly the same as for the ReggeWheeler package. But for now, I'll get started on the talk. So I'll start by introducing what is the MST method and what is the motivation for using it. So it offers a semi-analytic series solution to the radial Teukolsky and functions as a low frequency expansion. And we'll kind of see what all of that means shortly. So just a reminder of what these equations look like. We know that for spin weight 2, the Teukolsky equation describes perturbations to the Wall scalars, and that the ReggeWheeler equation describes perturbations to the metric. So they're obviously both very important in the context of black hole perturbation theory, which is what we're all here to do. So solving these things is what we'd like to do, and we've already seen a little bit of that. So these are quite difficult to solve analytically. Over past while, lots of people have made attempts, including Teukolsky and Lever, which usually involves a change of variables to make these equations a little more tangible. But we're going to look at the MST method, which does something similar. It uses a change of variables and has some very useful results. So the goal here is basically to solve these things analytically or semi-analytically. And I'm going to go through the derivation of obtaining the MST solution for the Teukolsky equation, mostly because that's what appears in the literature, and we'll see later on how we can obtain MST solutions for ReggeWheeler as well. And we're looking at both just the homogeneous case. So the first thing we might notice if we want to try and solve the Teukolsky equation is that we have a couple of singularities. We've got two regular singularities at the inner and outer horizons, as well as, excuse me, an irregular singularity at infinity. So any change of variables we might want to use is going to need to sort of capture those singularities. And another thing that we need to think about is the asymptotic behavior of the Teukolsky equation. So let's say we took the limit of this equation as r goes to infinity or to one of the horizons. The Teukolsky equation would simplify a lot, and the solutions that we would get would be a little bit like this. So r in and r up would be our two independent solutions, and these sort of are asymptotic behavior of the equation. We've got these sort of Penrose diagrams to sort of show what the boundary conditions sort of correspond to. I've just given r star the tortoise coordinate for both Kerr and Schwarzschild, if you're wondering why it's repeated. We'll see what this x is about shortly. So whatever solution we kind of come up with should really, we want it to recover this asymptotic behavior. So I'll show you how we derive the solution for the ingoing case, and the upgoing case is largely a similar procedure. So we might start off doing something like this, trying to capture the ingoing solution at the outer horizon. So we see that this factor here is just this one here. And as long as P in sort of behaves itself, this solution should recover the behavior at R plus. As I mentioned, we're going to want to use a change of variables to sort of deal with the singularities. and that looks like this. And so this is what x is defined as. Now this looks suspiciously like I've pulled a rabbit out of a hat, but this prefactor here is exactly the same as the prefactor there. Hopefully people can see my cursor. Let me know if you can. So we can actually derive this sort of prefactor when we look at the Teukolsky equation and see how we want to capture those poles. So it's not quite just coming out of thin air. This is the solution that we're going to go with, and we want to be able to solve now for P in. So to do that, we can go ahead and sort of change the variables of the Teukolsky equation and throw this solution into it and see what happens. And what we get is a perturbed hypergeometric equation. So how do I know that? Well, I wouldn't hold it against you if you didn't know what a hypergeometric equation looked like off the top of your head. You can always check it out on the DLMF if you're interested. But the right-hand side is of the standard form of a hypergeometric equation. And the right-hand side, with all these sort of powers of epsilon, looks sort of suspiciously like it's a perturbation in sort of powers of epsilon. So that's why we call it a perturbed hypergeometric equation. So we don't necessarily need to choose epsilon as small here, but we're going to exploit the fact that this looks like a perturbation in order to try and obtain semi-analytic expression. So we're going to go ahead and assume that epsilon is small, and this is sort of the basis of finding those semi-analytic expressions with the MST method. If we assume epsilon is small, epsilon is related to the frequency omega, if we're in the frequency domain, like this. So when I say small epsilon, really we're talking about a low frequency regime, which maybe is a little bit more restrictive, but any solution is a good solution. So we will go ahead and make this assumption. So I should talk about what is this lambda and nu here. Well, lambda is our sort of eigenvalue. Niels talked about yesterday the spin-weighted spheroidal harmonics. So you could use that package to calculate lambda numerically or otherwise. And nu here is this funny thing that we call the renormalized angular momentum. So there's a lot of analysis that I'm going to swiftly sweep under the rug here. But nu, we can see on both sides, it sort of appears on both sides of the equation in the same capacity. And it looks a little bit like this. So to leading order, it's just our L mode, but we have a second order correction. And this ensures that our right-hand side is indeed at least of order epsilon. So we can treat it like a perturbation. And the renormalized angular momentum also ensures that our MST series that we'll see shortly converges correctly. But I won't delve into the analysis too much on that. Okay, so the main point is that our Teukolsky equation is now a perturbed hypergeometric equation, and so its solution is a hypergeometric function. Why do we get this sort of series of hypergeometric functions, these series coefficients Fn? Well, hypergeometric functions obey recursion relations, which we can exploit. And so it turns out that the full solution will be a series solution where our series coefficients obey a recurrence relation. So I'm not going to state what lambda or alpha, beta, and gamma are, just because it would get a little bit messy, but they depend on our S, our epsilon, our nu, our L, and so on. So we can solve this, and with our assumption that we have a small frequency, we can get some semi-analytic expressions. So I'm just going to give a quick example of what these look like so you have an idea. And for the Schwarzschild case, for S is 0 and L is 2, we get these sort of expressions in terms of powers of epsilon. So there's two things that I'll talk about here. One is that if we say take F4, for example, we see that the leading order is e to the 4, F2 has leading order e to the 2, and it's kind of like a similar pattern for all values of n in the series. What this means is that if we wanted our solution to second order, for example, we would only need to include the first few terms in the sum, because second order doesn't appear in the higher sort of coefficients. That's a really nice property of the MST series. But the other thing that is worth mentioning is that while to get this sort of semi-analytic expressions, we needed the assumption of small frequency, when we don't necessarily need to do that if we want to say solve this numerically, for example, which is what the MST package does in the black hole perturbation toolkit. Okay, so if we solve for our series coefficients, then we've finished solving Pn. Remember, this was our sort of original function that we wanted to solve for, so we can sort of reconstruct our final solution. I'm just going to drop Lm omega because it's just going to get in the way a little bit, but the dependence is still there. So this is our final sort of ingoing solution. This is the MST series solution for the ingoing Teukolsky radial function. So a couple of things here. It should recover the correct asymptotic behavior on the outer horizon by construction. And it's valid almost over the entire domain. And that's sort of due to the property of how the hypergeometric function behaves. Now, if we wanted to get, for example, our incidence and reflection coefficients at scry or at infinity, we wouldn't be able to do that from this expression. So we're going to need to find another expression for the ingoing solution that is valid at infinity and that can sort of match the two different domains. But you follow a very similar procedure to obtain that expression. Okay, so you also follow a similar procedure for R up. What we would do is we choose a slightly different change of variables and make sure that we are capturing the different asymptotic behavior. And we would throw our sort of trial solution into the Teukolsky equation. We'd get a perturbed Coulomb equation or confluent hypergeometric functions, which is what this U is here. And again, solve a recurrence relation. So these coefficients happen to be the same, which is nice. So yeah, we've already done all the work for Rn, and it's kind of the same deal for R up. Again, it recovers the correct asymptotic behavior, and that analysis I said that I wouldn't go through. There's a lot of details there that you can look into to make sure that the series does converge. Okay, so let's see. Now that we have the Teukolsky solutions, or an MST version of those, we'd like to also get the ReggeWheeler solutions. So we could do the same thing. We could say, all right, gonna change the variables, see how the ReggeWheeler equation transforms, yada, yada, yada. But there's kind of a little bit of an easier way to do it, which is using the Chandrasekhar transformation. And what this allows us to do is it allows us to construct ReggeWheeler solutions from Teukolsky solutions. So this 0, -1, -2 refers to the spin weight. So if we have MST expressions for these guys here, the Teukolsky radial functions, then we can construct MST solutions for the ReggeWheeler master functions as well. And that's just a little bit easier than deriving it all again from scratch. So the results that we get there are very similar, actually, to what we saw before. We've got hypergeometric functions for the ingoing case. confluent hypergeometric functions for the outgoing case. And again, we have all of the nice properties that we need. Okay, so we've achieved our goal. We've got MST series solutions for ReggeWheeler and Teukolsky. And I'm just going to revisit the sort of reasons for using the MST method. Okay, so at the beginning of the talk, I said that it offers a semi-analytic solution to the radial Teukolsky and ReggeWheeler master equations as a low frequency expansion. And hopefully you can understand a little bit more about what I meant by that now. And one thing that's maybe worth noting is that in this low frequency regime for circular orbits, this is the same as for the post-Newtonian and post-Minkowskian regime. Some of you might say, okay, hang on a minute, we're doing black hole perturbation theory, we're interested in EMRIs, why are we talking about PN? Well, it's still good to be able to map different parts of different regimes, kind of stitch them together. But as I said, we weren't necessarily restricted to low frequencies, and the MST method also provides us with a new numerical tool, which is what the toolkit does. So why would we necessarily use MST numerical method over other numerical integration algorithms? Well, MST offers a really precise solution, though this is comes at the cost of speed. So it kind of just depends on what you want to do. Okay, so that's sort of it for the theory. What I might do is see if there's any questions in the chat at this moment before moving on. Actually can't quite tell.
So do you see the question in the chat by Amruta Sadhu?
I can't quite see it if the window's being a bit funny. Could you read it out to me?
Okay, yeah. So Amruta asks, you mentioned that to get to the coefficients, you don't need the assumption that epsilon is much smaller than 1. Mm-hmm. So where is the assumption coming into play, and is your solution valid for all epsilon?
Okay, so yeah, that's an interesting question. I think the main point is that to get the analytic expressions, you need that assumption. But to numerically solve the recurrence relation, just use sort of a standard algorithm there, which is in the code. So yeah, it depends on what you want to do. I hope that answers the question. But if not, we can certainly talk about it more.
So do I understand it correctly that you are kind of iterating for some of the coefficients and kind of converging to numerical values of these kind of Fn, right? Or...
I think so. For that particular the sort of numerical solver, I think Barry would be better able to answer that, not to throw him under the bus. But yeah, that's kind of the general idea.
So maybe can I have one more question at this point? Do I understand it correctly that you have to make a choice of a matching radius somewhere in the procedure, or?
Okay, so what the MST code actually does is say the expression that I had that was valid from R plus all the way almost to infinity. You can use this full expression pretty much, and then you can calculate the sort of say the reflection and transmission coefficients and use those separately to sort of finish off the solution. But yes, you could also match the two solutions, but that's not quite what we actually do in practice. Does that answer your question, Wojciech?
Yes, thanks.
Okay.
Okay, in the meantime, there was another question by Andrew Spires who said, "Hi, Leanne, does this solve the vacuum Teukolsky equation, or can it also solve for Teukolsky equation with a source?"
I should know the answer to this. I've only seen it done the homogeneous case, but I don't see why you couldn't then convolve it with a compact source.
So I'll be following up after Leanne with
sure.
a tutorial on actually constructing inhomogeneous solutions for a point particle case.
Okay, great. Thanks. So maybe we can proceed.
Sure. Thanks, Andrew, for your question as well. Okay, so let's see. Just before I start with the notebook tutorial, I'll just briefly talk about what the packages kind of do. So we've got the MST, Teukolsky, and ReggeWheeler packages that sort of compute these functions here. So the MST package computes the MST radial in and MST radial out functions, and these are exactly the ingoing and outgoing solutions to ReggeWheeler and Teukolsky that I just showed you. But we don't actually use this package as sort of a front-facing tool. We access it through the Teukolsky and ReggeWheeler packages. So say you wanted to calculate Teukolsky radial or ReggeWheeler radial for some set of parameters at some radius for the MST method. I believe the MST method is actually the default thing. And what these packages will do, they will access the MST code and calculate that. But you don't actually ever use this directly. So I'll be talking about using the ReggeWheeler package. And as you can already see, it's pretty much a copy and paste kind of a job, just replacing ReggeWheeler with Teukolsky and maybe adding in an extra parameter or two. So we'll just focus on this because the usage is very similar. And we'll look at the sort of numerical options and the MST options as well. Okay, so I am going to do a new share. Okay, so now would be a good time to open up your notebook, or maybe you don't have to right now. You can do that when we're looking at one of the exercises. So my contribution to this was really just the ReggeWheeler part of the MST code, but a lot of other people have contributed to this as well. So for installation, in case you weren't here yesterday, you might want to run some of these things. But if you've already done that, you can just go ahead and run the ReggeWheeler package. Okay, so let's have a look at the function usage. And yeah, it's worth pointing out that all of this is in the documentation as well. I just put it into sort of one cohesive tutorial. Okay, so how do we use this function? It needs an S, L, and omega value. The standard convention is that m equals 1. So let's just go ahead and define some parameters and see what happens when we call the function. So these, the outputs we get the ingoing solution and the outgoing solution. And again, these sort of diagrams to show us what the boundary conditions are like. If we maximize this, we can see, okay, we've got all of the details. We've got the domain, the eigenvalue, the transmission amplitude. For MST, the convention is usually that transmission is 1. You'll see these things are missing. I think this is a work in progress. You can see that we've got the MST method and that the renormalized angular momentum, that funny new thing that I was telling you about, is also calculated. And if you remember that to leading order, it was L plus higher order corrections. So if L is 2, our renormalized angular momentum is kind of close to 2, though that's sort of sensible. Okay, so how can we use this function? We could just call the sort of ingoing part like this. Most of the options should use strings and quotation marks, so just be careful of that. And let's say we want to call the function at a specific radius. So we could define some radius like that, and then we get our nice output, which is probably 30 digits or 32 digits, given the precision that we've set up there for omega. Okay, so we can also compute derivatives. What this does is takes a derivative of the MST series rather than a numerical derivative, just like that, using prime in the usual way. We could evaluate Rn at a bunch of different radii. That's fine. So all of that was sort of default MST. We might also want to use the numerical integration method. And the usage is like this. So we set the method to numerical integration, and we also require that we need to tell it what our domain is and our boundary conditions. So if we run that, we get our ingoing. We can see our domain is from 10 to 100 as we've set it. And if we just maximize that real quick, we can see that the method is numerical integration. Okay, what if we wanted that at a specific radius? Well, we do the same thing. Maybe I could have saved this as a variable, but oh well. So we could just specify some specific radius, and this is pretty much the same as what the MST method gave us, but there'll be some digits that are slightly different. Okay, let's say we wanted to specify different domains for outgoing and ingoing solutions. We could do it like this. So we say domain up and in is like this. And we can see for our ingoing, we're going from 3 to 10. And for our outgoing, we're having a radius of 10 to 100. Okay. And as I said before, we get a sort of, there's a trade-off depending on what you want to do between using the numerical method or the MST method. To get the other properties, we could just call Rn what is S, spin 2, and you can do that for all of the different properties as well. For example, what is our amplitude? Our transmission amplitude is 1. What about if we wanted to calculate our renormalized angular momentum separately from the code? Well, this is the function that we could use. Let's query that. These are the inputs that we need. We need SL, M, A, omega, and lambda. So if we're looking at just the Schwarzschild case, then we can set our sort of a sort of black hole angular momentum to 0 and just define a bunch of these things. And then let's see, what is the answer we get for the renormalized angular momentum? Well, that should be exactly the same as what it is calculated using the ReggeWheeler radial function. And we can see that is indeed the case. There's a couple of further options just for anyone who's interested in like your precision and your accuracy and things like this. And I believe it's been set up in such a way that it should sort of match the conventions that inbuilt mathematical functions will use. So, for example, we could set up these options. What is our precision goal and accuracy goal for the ingoing boundary conditions at radius 10, and it'll just give us something like that. So you have to play around with that. Okay, so now we know how the usage works. I'm going to do an example. Let's see, we want to compare the ReggeWheeler numerical integration method with MST and maybe also what we'd expect analytically as well. Okay, so For some reason, I have two of these. Let me just delete that. Okay, so in my talk a few minutes ago, I gave the asymptotic sort of conditions for the Teukolsky case. This is for the ReggeWheeler case, and they're a little bit more simple. So if we're plotting our ReggeWheeler functions for MST or the numerical case near these boundaries, we might expect to try and recover this behavior. Let's see an example of that. So we're going to first look at near scry. The behavior of psi up should be plus I omega r star, this guy here. And because we're looking at it at scry, remember r star and r will have similar behavior, so we don't need to worry too much about that. Let's go and see what happens. Does the numerical and the MST method compare with what we would expect? So let's just go ahead and run this. So psi in will be the ingoing case, psi up will be the outgoing case, and we're going to define psi up scry to sort of make a table of values for large R being our scry in this case. We run that. So that will be our MST because MST is default here. And then we could get our numerical integration data as well. So let's go ahead and plot that and see how they compare. Great. So the MST method, I think, are going to be the dots, and the numerical method is the joined line, and we can see they overlay very nicely at scry for the outgoing case, which is great. How do these things compare to our sort of predicted behavior, e to the I omega star? Well, we might want to define what R star is to be able to do that. So I'm just going to run that. And if we compare that, now we've just overlaid, if you can see the kind of gray dots, that's going to be our sort of analytic prediction. And we can see that it all compares very nicely. So now what I'm going to do is I'll invite you to either play around with the black hole parameters, see what different plots you can come up with, or if you can try this example here, that near the horizon R+, see if you can compare the MST and numerical solutions with the predicted behavior. So I might give people just a few minutes to work on that, and I'll sort of keep the window open for questions, and then I'll go through the solutions. I think we have about 10 minutes. Does that sound good? Download it and follow along, okay?
Okay, so we have had some questions in the meantime. We have had one question on Slack, and Jonathan Thompson asked, is it a simple matter to get Zerili from MST RW using the differential relations on the series expansion, assuming vacuum?
I want to say yes, though I haven't seen it done. Yeah, I guess if you can just transform to Zerili a little bit like we did with the Chandrasekhar transformation, why not? Though maybe someone else has a bit more expertise or knowledge on that, but my feeling would be that we could do it.
There was also a little bit of a discussion about different effective potentials, but I think that also boundary conditions, but I think Barry and Niels are on the duty answering those questions directly in the
okay. Thank you very much for that.
Yeah.
Yeah, if anyone has any questions about the code so far as well, feel free to ask.
Okay, so now we have another question from Hung Yi. Is there any reason we are especially interested in radial Teukolsky equation and not the angular one?
Yeah, I guess the radial Teukolsky equation is what gets you your perturbed file scalars, right? So if you want to use those at all, it's a good thing to have. But yeah, as Niels talked about with the sort of this spin-weighted spheroidal harmonic eigenvalue and all of that, you can get those. Sorry, I think Barry was going to say something there.
I was just going to say exactly what you said, that the angular equation is covered by the spin-weighted spheroidal harmonics package.
Mm-hmm. Yeah. I'll just give people a couple of minutes to have a think about that exercise problem.
So we have another question from Soichiro Isoyama in the chat. What is the efficiency of the MST module? Is it as fast as the numerical integration given the same precision?
I think not. There are tests on that are done in the toolkit for these kinds of things, though I haven't actually looked at that at all. I think again, Barry would be more knowledgeable on the sort of timings of things.
I think you had it up further up in your slides somewhere that if you want to evaluate the radial function very accurately at a single point, MST is probably the way to go because it's very accurate but slower, whereas the numerical integration very efficiently evaluates across a whole range of radii, but not quite as accurately. So certainly if you want to go beyond machine precision, the MST method is the way to go.
Do we have any idea of sort of how fast is the differences quantitatively?
It's significant. I don't know. Try it out and let me know.
Sure. But yeah, it's a good question. Numerical would generally be faster, and those tests are worthwhile looking into. Okay. Was there another question just there, or?
So there's yet another question about precision. So Zachary Nasipak is asking, what is the typical precision of the numerical integration, 6 digits machine precision? I think that probably depends on how you set up your numerical integration, right?
Yeah, and that I'm not sure because I wasn't working on the sort of numerical integration of it. But yeah, I think it just depends on what you put in.
Yeah, so to follow up, the ReggeWheeler radial, the function has options to it, the usual ones: precision goal, accuracy goal, and working precision.
Yeah, I mentioned those earlier.
Yeah, and so the defaults are working precision is machine precision, so that's 16 digits. And the accuracy goal and the precision goal is half of that, so 8 digits. If you don't specify anything else, that's what you should expect to get.
Okay, so I'm gonna continue on with the tutorial now that people have had some time, hopefully, to think about it. So I left the sort of case for the horizon for psi in later because it's a little bit harder. Because near the horizon, we need to be careful of the sort of R star behavior. So if we want R in terms of R star, this is sort of what we what we can get. So I'm just going to go ahead and run that. So if we want to define the ingoing MST data on the horizon, this is what we can do, going from R star from -100 to 0. And then for the numerical data, we can do something similar. Notice how I've only gone from -50 to 0 here, and we'll talk about that in a second. So if we go and compare those, we see that the data match, and maybe I could try and extend this a little bit, let's say to 70, but I think it, oh, it's because I haven't changed it. Silly. Okay, yeah, so it kind of like starts to struggle a little bit, and you could play around with pushing those limits. So I've just said that MST and numerical methods agree near H somewhat. Okay, so does this agree with the sort of expected asymptotic behavior? We could go ahead and plot that, and the answer is yes, mostly, and then we kind of see a little bit of deviation as we get very close to 0. Okay, so hopefully you kind of had a nice go of doing that. I think I only have a couple more minutes, so I won't go through a full example, but in this section, if you want to take a look later, we have a comparison with ReggeWheeler numerical integration method with MST for the field equations. So before here, we were looking at the sort of boundary conditions, and we can try and see that the MST method and so on satisfy the ReggeWheeler equations. So I guess I could do this really quickly. If we run our ReggeWheeler equation, save our values, let's see, we could run these guys here. It's a little slow. Let me put it up to 20. Good. So you could use like an interpolation method if you liked, or you could just create data points. And we get this kind of a mess, but we see that it's all very close to 0. So we're satisfying our ReggeWheeler equation to reasonable accuracy. So the rest of these things down here are sort of a copy and paste job that I've left empty, or no, this is my solutions. Your version should be empty. And you could try out something similar, but for the numerical and the upgoing cases, and also calculating the retarded solution for a circular orbit using the MST method and numerical integration method. Okay, so I think I'm just about out of time, so I'll leave it there. Thank you.
Great. So thanks a lot for the talk. I finally understand how MST actually works, you know.
Oh, I'm so glad.
Yeah. It was great. I think all of the questions you have answered during the talk, and thanks again.
Great. Okay. I'll stop sharing my screen then, but of course, if there's any questions later, I'd be happy to answer.
So once again, you can continue the discussion on Slack. I will probably have some follow-up, and now we should have the talk of Barry, who should talk about Teukolsky and extended source calculations. So there were also some questions which were essentially for Barry or will be answered by Barry's talk, so stay tuned. Okay.
Okay, thanks very much. I've shared the notebook here. Can everyone see that? Is it clear enough? Is it the text big enough to read? Okay, great. So this notebook you can also download from the conference website. Up there's a completed version of the notebook, but the one I'm going to go through now has had all of the Mathematica code removed. And we're going to go through this together and actually do a full calculation end to end using the toolkit, in particular using the Mathematica parts of the toolkit. And so the calculation I thought we'd do is to compute the energy, the flux of energy through the horizon and through infinity from a point particle in a circular orbit around a Schwarzschild black hole. And this is a nice example because it actually allows us to use all the parts of the toolkit that we have. And it also touches on one of the questions earlier about constructing inhomogeneous solutions. Okay, so the goal here is that we want to compute the fluxes. The way we're going to achieve that is by solving the Teukolsky equation, the inhomogeneous Teukolsky equation, where you have a stress energy tensor given by a point particle. And we're going to do it for Schwarzschild spacetime for simplicity here, although you could go through the same process relatively easily for Kerr. Okay, so we're talking about Schwarzschild spacetime. So the first thing we're going to want to do is to actually load the Schwarzschild spacetime. And the way we're going to do that is using the general relativity tensors package. Okay, so we load the package. We then load the Schwarzschild metric using 2 metric, as Seth showed us yesterday. And then I'll just print it out as well. So we can see for ourselves that that really is the Schwarzschild metric in standard coordinates. The second thing we're going to need later on is the square root of the negative of the determinant of the metric. So let's just define that as well for now. I'll call it square root det g. And that's just going to be, I'll simplify it. It's the square root of minus the determinant of the matrix of components of the metric. So the tensor values of g. And I'll tell Mathematica things that we know about the Schwarzschild spacetime. For example, r is greater than 0 and theta is between pi, 0 and pi. Okay, and you just get the expected determinant of the metric, r squared sine theta. So that's part 1. Next thing we're going to want to do is construct a source for the Teukolsky equation. And I'm going to build that up in a few steps. And before we actually go on to the stress energy tensor itself, I just want to highlight that the way you get the source for the Teukolsky equation from the stress energy is by projecting onto a tetrad and then acting on those tetrad components of the stress energy tensor with certain differential operators. And it's worth having a look at those differential operators in more detail before we actually go on to doing the stress energy tensor. So there are 2 sets of operators. One set are, in the Schwarzschild case, are just on the 2 sphere, so on the theta and phi directions. And those can be thought of as spin raising and lowering operators. So what do I mean by that? Well, these are the operators. This is one way to write them here. They're called eth and eth primed. That's what this symbol here is. It's kind of weird D with a line through it. And those operators are just defined to be the projected partial derivatives. A projected partial derivative where here the m vector is a vector defined on the sphere. We're going to define that a little bit later. And then you also have 2 terms here, one involving b plus s, where b is the boost weight of whatever you're acting on, and s is the spin weight of whatever you're acting on, times a coefficient beta, and another term b minus s times coefficient beta primed complex conjugated. So I'm using an overbar to denote complex conjugation here. And likewise, eth primed is also given in terms of similar operator. Okay, so these things, beta and beta primed, are called spin coefficients. They depend on particularly how you choose a tetrad, but there's a well-known tetrad called Kinnersley tetrad, and we'll see in a minute what they look like. But just to give you a preview, if you go to the Kinnersley tetrad and you think about Schwarzschild spacetime, then you have a specific choice of M here, and a specific choice of beta. Then if you act on a spin-weighted spherical harmonic, Y SLM, well, that has a particular spin weight S. It doesn't have any boost weight, so B is 0. S is whatever the S is of the thing that you're acting on. And so these operators take the explicit form that they take a spin weight S harmonic, F takes a spin weight S harmonic, and turns it into a spin weight S plus 1 harmonic plus a multiplicative factor involving L, S, and R, the radius. And similarly, S primed, acting on the spin weighted harmonic of spin weight S, brings you down by 1. So it brings you to an S minus 1 spin weight harmonic with another one of these factors. So I'm telling you this now, but actually we can check this explicitly. And the way we're going to do that is we're going to define these two operators in Mathematica. So I'm going to define an eth operator. It's going to act on scalars. We're only going to be differentiating scalars here, or spin weighted scalars. They might have a spin weight S and a boost weight B. And we're just going to take exactly the definition above. And the great thing is that general relativity tensors gives us a lot of the things we need. For example, Kinnersley derivative for Schwarzschild. And we want delta is the one projected along the M direction. So this term here is just the M dot partial derivative of the scalar. We then have minus B plus S times the spin coefficient. But again, general relativity tensors has those built in. And it's the beta coefficient that we want. And we also have a term involving B minus S times the other spin coefficient, which is, if you look up above, it's beta primed bar. Beta primed is in fact minus alpha. I've taken account of the minus sign already. So this is just alpha. And then the bar means complex conjugation, which in general relativity tensors means you need to put a third argument here, true, which says that this is the complex conjugate of this spin coefficient. And this thing all multiplies the scalar. Okay, so that's eth. Eth prime is going to be very similar. So I'll just copy the line from above and I'll change the things I need to change. Instead of delta, it's delta star. Instead of beta, it's beta primed, which is alpha. And instead of beta primed bar, it's beta bar. So it's just beta bar. Okay, so now we have at hand spin raising and lowering operators defined in Mathematica. We can see what these things look like when they act on a function. So for example, eth acting on an arbitrary function of theta and phi of spin weight S and boost weight B. If we simplify it as well, it's just something involving first derivatives with respect to theta, first derivatives with respect to phi, and some things involving cosine theta and cosec theta. And there's that factor of 1 over root 2r there as well. And similarly, eth primed acting on an arbitrary function of theta and phi gives you a similar type of operator. So I said above that actually this is a nice identity to use, that these operators satisfy. Let's actually check that. And the way we're going to check that is using another part of the toolkit. the spin-weighted toroidal harmonics package. And what I'll do is I'll check that eth of a spin-weighted spherical harmonic y of some given S, L, M as a function of theta and phi is really equal to what we had above. If I can fit it in. Hopefully everyone can still see that. I said that that was actually equal to minus 1 over root 2 times r times that factor of root L plus 1 minus have I got things the wrong way around? I'm slightly worried I've got things the wrong way around now, but let me just keep going anyway. Times a spin-weighted spherical harmonic. And this time the harmonic has gone up by 1. So let's check that for a bunch of values of S from minus 2 to 2, L, a bunch of values of L from, well, you can't have L being less than S. So starting from there up to 4, and a bunch of values of M. M can be between minus L and plus L. And we'll get Mathematica to do the simplification because you get some trig functions coming in that aren't obviously 0. Okay. Oops. When I took my raising operator, I needed to specify the spin weight of the thing acting on. The harmonics have spin weight S and boost weight 0. And so now that should produce a whole load of answers to tell us that all of these equalities hold. Yes, okay, great. And you can see it said that this equality is true for all these different values of S, L, and M. And I'm not going to type it in because it's just exactly the same, but you can also check the spin lowering operator has the same property that we've defined. And we just run it to check that we do indeed satisfy those properties. And yes, they do. So that's great. We've been able to use the spin-weighted spherical harmonic that's defined in the spin-weighted toroidal harmonics package to check our calculations, to check that we really do have those identities. And these are checked, using mathematics because symbolic algebra. So for arbitrary theta and phi. So that's the first part of what we're going to need for constructing a source to the Teukolsky equation. We have these spin raising and lowering operators, these angular operators. The other thing you're going to need is you're going to need to take t and r derivatives. And these are nicely packaged up in what are called boost raising and lowering operators. So these have definitions that are somewhat similar to the spin raising and lowering ones. They involve this other weird symbol called Thorn. But all you need to think about it is that it's essentially a derivative along the L direction, where L is one of the other legs of the Kinnersley tetrad, plus a couple of terms involving the boost and spin weights, B and S, times these epsilons, epsilon bar, epsilon primed, and epsilon prime bar, which are again other spin coefficients. So let's define those operators. So Thorn acts on something, a scalar of spin weight S, boost weight B, and it's just a Kinnersley derivative in Schwarzschild. It's called D in the general relativity tensors package, acting on that scalar, minus B plus S times epsilon. So the epsilon spin coefficient plus B minus S times the epsilon bar, the complex conjugate of epsilon. And again, we specify complex conjugation by giving true to the third argument. And that is multiplied by the scalar. Likewise, we can define Thorne primed, and all we do is we go back and change our operators. So this becomes D becomes delta in here, and our spin coefficients become gamma and gamma bar. Yes. Okay. And we're going to use these later, but let's for now just look at what these operators actually do when acting on a scalar function of T and R of spin weight S and boost weight B. Well, Thorne, I'm going to simplify it a little bit using Mathematica. Using collect. Thorne is just DDR minus 1 over F ddt. And Thorne primed is something involving 1/2 DDR here, plus 1/2 F ddt, plus an extra term involving B, the boost weight. Okay, so now we have 4 operators, F prime, Thorne prime. These are the spin raising and lowering operators. And that's all we're going to need in order to construct a source for the Teukolsky equation. Just check how I'm doing time. Okay, great. So let's go on and actually try and use these to construct a source for the Teukolsky equation. And in order to do that, what we're going to need first is the stress energy tensor. And in particular, we're going to think about the stress energy tensor for a point particle, which is given by this expression here. The stress energy tensor is just a product of 3 delta functions, a delta in R here, a delta in theta, and a delta in phi. It involves the 4 velocity, 2 copies of the 4 velocity of the particle's whirl line, and there's a 1 over ut, the t component of the 4 velocity here, and there's a factor of that determinant of the metric, square root of the determinant of the metric in there as well. We're going to use a little trick to do an expansion of this into spherical harmonics or spin-weighted spherical harmonics, depending on the case. And the trick we're going to use is the fact that the spherical harmonics satisfy a particular completeness relation, which is that the product of a delta function in theta and a delta function in phi, and this is also actually a delta of cosine theta, which absorbs in the sine theta from the root g down here, that this product is in fact the sum of products of spherical harmonics, spin-weighted spherical harmonics here with their complex conjugates here of any spin weight u onto s. And so in fact, we can rewrite this point particle stress energy tensor above as a sum over spherical harmonics of spherical harmonic modes of that point particle stress tensor. And I haven't been particular here about what I mean by S, what S value I'm going to use. Okay, so now we want to actually do this for a specific case. So what we're going to consider is the case of a circular orbit in Schwarzschild spacetime. So we want to know about what circular orbits in Schwarzschild. A nice easy way to do that is to use the Kerr GD6 package. I'm going to just set m equals 1, and I'm going to only assume that the radius of the orbit R0 is greater than 3, because you can't have circular orbits less than that. And we're going to ask the Kerr GD6 package to tell us about the orbit. Well, the properties of the orbit that we'd like to use are the fact that it has 2 constants of motion, as we saw with in Martin's talk yesterday. I need to specify A, P, E, and X, like Martin said yesterday. So A is the spin of the black hole, which is 0 for Schwarzschild. P is the size of the orbit, which in a circular orbit case is just R0. E is the eccentricity, 0, because it's a circular orbit. And X is the inclination, which 1 corresponds to equatorial motion. So if we run this, we see we get the energy and the angular momentum. Well, those are also, in fact, if you think about the 4 velocity, well, that just has covariant components given by minus E for the T component, 0 for the R and theta components, and L for the phi components. So in fact, those are the covariant components of the 4 velocity. So let's use those to define a tensor. I'm going to call it U, defined with respect to the metric G. And I've given it the components here, and then I need to specify that these are the covariant components, downstairs components of that tensor. And I'll save that in U. And I'll just print it out as well. Okay, so this is my 4 velocity with downstairs components given by what we have here. Okay, with that at hand, we're ready to go computing the stress energy tensor. All we do is we take in our expression from above. I'm just going to focus on a specific LM mode. So I'm just going to take the thing inside the parenthesis here. I'm going to type that in. So it's just minus, it's a delta function in R times a 1 over R squared. That's the root G factor. There's a factor of UT. And then we're going to have U alpha and U beta. Now, in general relativity tensors, there's a way to turn a product of tensors into a tensor. And the way we do that is we use merge tensors. And we actually want to expand out the components of this thing. So I'm going to use tensor values on that. So these are the components of this tensor that you form from the product of these 2 vectors. And we'll also have that factor of this, the conjugate. There's a bar here, which is a little bit hard to see, of the spin weighted spherical harmonic. So I'm just going to put that in for now as Y bar. And it's at theta naught and phi naught, which for an orbit on the equatorial plane, theta is pi by 2, and phi is just the orbital frequency omega times t. Okay. And in fact, because of this delta function here, I can set R equals R naught without loss of generality. And I will now simplify that. Great. And I'll actually define a tensor T with those components. With the indices downstairs. Okay. And I don't want to set R equals R naught inside the delta function. Sorry about that. So I just put some brackets around. Okay. I guess I've got my comments in the wrong places, but there we go. Okay, so this is now the stress energy tensor. Can everyone still see this? Is it a little bit small?
I think it's
a thumbs up for yes, a thumbs down for no. I can see your video.
I think it's fine, but maybe like this small matrix is not visible anymore.
Okay, let me just make it a little bit bigger here. There. Okay, so these are the components with indices downstairs of the stress energy tensor for a point particle. What we need to do now is take this and convert it into a source for the Teukolsky equation. The first step in that process is to project onto a tetrad. So these are the components with respect to the normal coordinates, t, r, theta, and phi. We'd like to obtain the Kinnersley tetrad components by projecting this tensor onto the Kinnersley tetrad. And we're also going to exploit the fact that these tetrad components have particular spin and boost weights associated with them. That's going to be important when we choose what we mean by S in the spin-weighted harmonic above. Okay, so the first thing we need is the Kinnersley tetrad. It's a tetrad set of 4 vectors, L, N, M, and M bar. And we're just going to use the fact that the general relativity tensors has this built in. Okay, so that's our Kinnersley tetrad. General relativity tensors denotes complex conjugation with a star, an asterisk. Okay, so now the NN component of the stress energy tensor is just what you get by taking the stress energy and projecting with N twice. Okay, so we're going to turn this product of a tensor with 2 vectors into a scalar by using merge tensors. And I'm interested in the explicit value, so I'll use tensor values. So that is the NN component of the stress energy tensor. Now you can see, actually it's not so critical in here, but it will be useful later on. So let me leave that for the moment as the NN, we'll simplify that. Okay, we can do the same thing with NM bar. And all we do is we just use M bar, NM bar in here instead of NM. And in this one now you can see what I was going to say before, which is that this thing depends on R naught, but it also depends on R. It would be nice to not have that dependence on R explicit, because we have the delta function. We can do that. We can just set this R equal to R naught. And the way we do that in Mathematica is if you have some arbitrary thing multiplying by a delta of R minus R naught, then you want that to go to X, that thing with R going to R naught times the delta function. And you also see we have a factor of theta here, but we know that theta has been pi by 2 for the equatorial case. And I'll put the simplify outside. And so this is now our NM bar component of the stress energy tensor. We can do the exact same thing, but with the M bar component. All we do is put M bar in here and it pops out. Okay, so we now, I'll make this a little bit smaller again so I can fit it on the screen. We now have our 3 components of the stress energy tensor, our 3 tetrad components that we're going to need to construct a source for psi4. There are obviously other components of the stress energy tensor that you could construct, but they don't appear in the source for psi4. Some of them appear in the source for psi0. Okay, and just to remind you that we have not yet said anything about the spin weight S, although we will be using the fact that these 3 things transform as functions with particular spin and boost weights. In particular, these are the ones. Yeah, so NN is essentially S equals 0, it's a scalar. NM bar is like a vector, S equals -1, and M bar is S equals -2, it's a tensor. Okay, so we have the tetrad components of the stress energy tensor. Next up, we need to compute the source for the Teukolsky equation. And we now have all the bits we need to do that. we have an expression for the source for the Teukolsky equation given here. You can see that this involves TNM bar, TNN bar appearing again there, and TM bar M bar. So they're the three tetra components of the stress energy that we had. And you can also see that involves these operators, eth prime, Thorne primed and eth primed, appearing a couple of times. These were the spin and boost raising and lowering operators that we saw earlier on. And the last thing it involves is a couple of these other Greek letters, tau, tau primed, tau bar, and tau bar primed. Okay. So these are all these taus and rhos are other spin coefficients, which general relativity tensors knows about. Now, so what we're going to do is we're going to work out this differential operator acting on these tetra components to get this script dt. This is the source for the Teukolsky equation. Things are a little bit simple in Schwarzschild, in particular because in that case, the sum of the coefficients are 0. In particular, tau is 0. So that means that these terms vanish. And, well, sorry, this term vanishes, but also tau primed, which is pi, is 0. So anything in here involving tau and tau primed is 0. So all of those are 0, and that one is 0. And so then, and also we have the fact that we've already seen that these operators here, eth primed, acting on spin weighted harmonics, just acted as spin lowering operators. Okay, so we're going to use that to make things a little bit simpler for us, although you don't necessarily need to do that. Okay, so what I'm going to do is I'm going to split this calculation out into 3 parts. I'm going to split it out into a part that involves just TNN. I'm going to call that T0. Essentially, the 0 just comes from the fact that it's because TNN is a spin 0 thing. I'm going to do a spin and a T1 in a little while, which corresponds to the NM bar pieces. So these two. And then I'm going to do a T2, which is the M bar, M bar. But let's start off with T0. Sorry, I'm just changing the size on the fly here to make sure everyone can see it. Okay, so what is T0? Well, that's just going to be eth primed and then zeros. And then there's another eth primed here, and there's a minus sign acting on TNN. Okay, well, we saw already that eth primed just gives you a factor of 1 over root 2 times r, and we've got 2 of them in here, so it's going to be 2 of those. We then have those factors of the square roots of L minus LL plus 1 minus SS plus 1. And one of those is going to be acting on, I'm going to treat TNN as a spin 0 thing. So I'm going to use a spin 0 harmonic in there. So that's going to have an S equals 0 the first time eth is acting on it. And then it's just L plus 1, LL plus 1 minus S minus 1. So that's the first time eth here acts on a spin 0 harmonic. You get this factor. You have it also acting a second time. I'll have to make it smaller to fit in. The second time, you've turned that spin 0 harmonic into a spin minus 1 harmonic. So now you're acting with the second one on a spin minus 1 harmonic. So you have an S equals minus 1 in here times this factor. We've now taken care of both of these differential operators, the 2 eth primes, and all we're left with is TNN. Okay, And so this is our T0. This is one part of the source for the Teukolsky equation. We can go through the same process now with the what I'm going to call T1. And that's going to be the NM bar piece. And if you look at what's involved there, well, there's a spin lowering operator. So that's going to give us a 1 over root 2r. And there is also a Thorne primed and this rho bar primed. Now we already have defined these Thorne primed operators, so all we need is the rho operators. Again, we can get those from general relativity tensors. I think I'm starting to run out of time, so I'm going to start just copying those in because we've seen how to do this already. So rho primed and rho bar primed are just particular spin coefficients. And likewise, because the process is more or less is exactly the same as before, I'm just going to copy in the answer here. So you can see now I have got my 1 over root 2r. I've got this factor of L plus 1 minus SS minus 1 from the spin lowering operator. And then I have the Thorne primed minus 2 rho bar primed operator acting on T and M bar. And then you also have a second term here, which is Thorne primed minus 4 rho primed minus rho primed bar. So that's the second half. Okay, and that's T1. I'm also going to use the fact that the derivative with respect to phi of the spherical harmonic can be rewritten as Im, or of the conjugate of the harmonic is just minus Im times the harmonic. And in this case, I'm also setting specifically the fact that this Tnm bar has been decomposed into spin weight minus 1 spherical harmonics. Yes. And I've just realized that I should have done the same earlier on here, because the T0 is involves spin weight 0 harmonics. And then I can do exactly the same thing with T2. Okay, and this is just the same business again, but for the M bar piece. Okay, so we now have a source for the Teukolsky equation. How do we construct inhomogeneous solutions to an ODE? Well, what we do is we can use variation of parameters. In particular, if you have homogeneous solutions R in and R up, you can construct the inhomogeneous solution by computing these weighting coefficients C in and C up and taking a linear combination. And where these C ins and C ups are just given by integrating against the source that we've just computed. The C in is obtained by integrating the up solution from infinity down to a certain radius R, divided by the Wronskian times delta, where delta I'll define in a second, and likewise C up is defined similarly. So we want to compute these C's, and then we're done. We'll use a trick, which is the fact that the actually delta to the S plus 1 times the Wronskian is constant, so it can be pulled outside of the integral. Okay, so what is delta? It's just the delta that you would have in the Kerr metric. It's R times R minus 2m. I've said m equals 1, so it's just R times R minus 2. And we'll also use sigma from the Kerr sigma, which in the Schwarzschild case is just R squared. Okay, well, what do we need to do? We need to do these integrals. So we need to integrate. Oops. Our radial function, just call it R of R, times, I'm going to split it into the three pieces, T0, T1, and T2 again. We're going to have a few factors to include that come from including things like root G and overall factors from various conventions. So there's a -4, there's a delta to the -2. These just are related to the conventions that we have for the Weil scalar psi4. There's also a factor of rho r to the 4th that you need to put in. And so now this is the integrand that we want to integrate excluding the bit involving delta ds plus 1 times the Wronskian, because that's a constant. Okay, so this thing here looks like this. We're going to want to integrate a delta function. So let's turn this delta into something Mathematica knows is a real delta function, a Dirac delta. Okay, and because I'm running low on time, I'm just going to copy in the line again. You can see it's the same. I'm just integrating the source from r equals, well, I'm integrating it over everywhere. It'll just pick up the bit from the delta function where that has support. And that'll give us our C0 weighting coefficient. And likewise, you can do the same for C1 coming from T1 and C2 coming from T2. Okay, so we're almost done. In the last 3 minutes, I will try to show you how we can actually use this now to do a numerical calculation of the flux. So what we need in here, you'll see these weighting coefficients involve r's here and r primes. These are solutions to the homogeneous Teukolsky equation. And we know how to get them. What we can do is we can use the Teukolsky package that Leanne just showed us. Okay, again, in the interest of time, I'm just going to copy in a few parameters here. We're going to look at the 2-2 mode for s equals -2 for psi4, spin 0. I'm going to do an orbit of radius 10. The frequency that we're going to be interested in is a multiple of the orbital frequency here. And I'm going to also have this delta. I will compute, just like Leanne showed us, solution for the ReggeWheeler case, solutions to the homogeneous Teukolsky equation corresponding to the in and the up solutions. The Wronskian is just r in times r up primed minus r up times r in primed. This is the invariant Wronskian, that thing that's constant, so I'm including the factor of delta to the s plus 1 as well. And that's what that value is. Then the weighting coefficients are just obtained by adding the c's together and dividing by that invariant Wronskian and substituting in the value for the spin weighted harmonic. So there are 3 weighting coefficients corresponding to, sorry, there are 2 corresponding to C in and C up. They're given here. And now we've constructed inhomogeneous solutions to this Teukolsky equation. In fact, I could have saved you this entire talk and just told you that there is one command in the toolkit to do exactly that, which is called Teukolsky point particle mode. And if I make it slightly smaller, you can see that I've gone wrong somewhere here. That should have amplitudes here at infinity and the horizon, which are should match these C's. Now they don't, and I will follow that up afterwards and check. Oh no, there's a difference of a factor of 2 pi. I remember. And so if we actually compare the amplitudes that the toolkit has computed, these values here and here, these are exactly the weighting coefficients up to a factor of 2 pi, which is just a difference in conventions. And you can check that they do agree with each other. So I realize I'm running out of time. I've run out of time. So let me finish up by showing you the fluxes. Well, the fluxes are easy to compute once you have the asymptotic amplitudes. The flux through infinity is just the up amplitude squared plus a few factors. And the flux through the horizon is similarly the in amplitude squared plus a few factors. And just like with the inhomogeneous solutions themselves, the Teukolsky package already has those built in. And you can see that it gives exactly the same flux through infinity and through the horizon. And the very last thing to say is that you can do the same thing with the angular momentum flux. Okay, I am out of time, so I'm going to leave it there. If you look at the notebook online, you'll see that there are comparisons with the same calculation done in the ReggeWheeler gauge using the ReggeWheeler package. And there is also a comparison against post-Newtonian approximations to these things, which is done using the PostNewtonianSelfForce package. So that brings together all of the package that we have. And there's an updated version of this notebook I'll send afterwards that also has an exercise for the keen participant to do at home. Okay, I'll leave it there.
Okay, great. Thanks, Barry. I think this was also a great exercise for general relativity tensors. I'm afraid that we should probably go forward to showcases. So there are some questions in the chat that you can probably answer.
Yeah, I can answer them afterwards. Sure.
And let's see. So we should now have the showcases. I will just well, maybe I will just start saying the names. Is Sebastiano ready? Sebastiano Bernuzzi for his first talk.
Yeah, I'm here.
Hi. So can you maybe share your screen with us and show us very quickly your projects?
So I get a message saying that the host disabled participant shared screening.
So maybe that's a question for Barry.
Okay, let me just check.
But I also sent my slides, so
you should be able to do it now. Try it again.
Yep. Can you see something?
Yes, we can see that.
Okay.
Okay, so a reminder, you have 5 minutes. So
yeah, I'll try to be very brief.
okay.
No. Okay. So I'm Sebastiano Bernuzzi from Vienna, and what I wanted to do is introduce a tool that we have developed in the past with the people that you see on the first slide. And you will hear much more about applications in the talk tomorrow by Alessandro Nagar. Here I'm just giving some technical detail about the infrastructure. So I'm talking about time domain solvers for the ReggeWheeler Zerilli and the Teukolsky equations with test particle or better test black hole, as we like to call them, on generic orbits. So the main motivation to do this for us was to support effective one-body waveform developments in first instance. So in particular to check and to develop the analytical resound waveform that we use for modeling gravitational wave from binary black hole, of course in the limit where the mass ratio is large. So the symmetric mass ratio goes to 0. And we have used this in particular to inform this model that we developed in this limit, where usually you introduce numerical relativity information. Here, of course, there's no numerical relativity in this regime. So we have used that solver to calculate the waveform. We also have some application about gravitational recoil. And also an important topic is to study how quasi-normal mode are excited in mergers. And finally, there is a nice work by Eno Harms about Kerr-Tails, where we basically reproduce all the possible analytical results using a highly accurate code, in this case with spectral method, and but it's basically the same. So the
Oh, sorry, Sebastiano, I think that we are not seeing what you are seeing. We are just seeing like you just before you started the presentation. So maybe there's some.
Okay. So let me now.
We see what you are seeing. Yeah. So maybe you can just keep it in this window and we will just watch it like this.
Okay, let me try to switch off this and switch in this presentation.
It looks like it's just not tracking the full screen. So if you just keep it in the window version, it probably will work.
Okay. Now? Okay.
Now we are seeing.
Let me try again. Sorry for this. Perhaps I don't present it. I simply show the slides without presentation. Okay, now I have. How about now?
No, we see. But perhaps.
It seems you're no longer sharing your screen.
Okay. Let me try again. How about now?
Yeah, now it's good.
Okay, so I've just shown this slide. Just talk about this name. I was on this page where I was. This is a summary of the application. So some of the application that for which we have used this code. So the main technical part of this code, that's what I want to discuss now, is the use of hyperboloid and horizon penetrating slicing of care in general. So this is a generic formalism developed by Zenginoglu, where you make a coordinate transformation, specify certain height function h, and an arbitrary conformal compactification factor. And if they have some properties, then you can achieve actually scribe fixing on any stationary background. In particular, in one of this work that we have done, we have realized that there's a simple way to specify the H function or better its derivative, and that's by demanding that, say, the null rays in the original and the new coordinate remain the same. And this basically closes the formula with the concrete prescription. And I would say differently from the nonlinear GR case, this problem in perturbation theory is essentially solved. For application, this is very nice because you can include both the horizon and scry in your computational domain. And so you can calculate fluxes and waveform at these two pieces in these two regions where they should be calculated. And also it simplifies a lot the treatment of boundary condition because you don't need any boundary conditions if you apply this formula. So you see in this picture on the right, the characteristic speed simply goes to 0 where they have to go to 0. So whatever wave they reaches either the horizon or scry, it simply reduces locally to the advection equation and is simply transported out. So this is the key technical part of implementation of this Teukolsky solver, which is called Teukode. So it solves the M azimuthal decomposed 2+1D Teukolsky equation using this particular coordinate. So it implements a generic source in the sense that so it's not only point particle, but we can have spinning particles, so spinning bodies, as Georgios would say. So it's completely generic in the sense that you can put any input any generic orbit, and you will get the M waveform, the M psi4, the M component of the psi4 azimuthal decomposition. It uses either Gaussian regularized or discrete Dirac function to represent the particle. And well, the rest is pretty standard. It's method of lines, high order discretization. It's fully parallelized. And you can use more than 1,000 cube grids or even larger, we had you can push this without any problem. It's unigrid, so it parallelized trivially. So this is not yet part of the black hole perturbation toolkit. And it's not public formally. The reason is that we never needed, but also we never bothered to check for memory leaks or stuff like that. So we really want to release something that we are not sure it's bulletproof. But nonetheless, this is open to interested people, so you can get in contact with me and I can give you access. Georgios is using this for waveform from chaotic orbits, and it is also used for the development of binary black hole waveforms, like the famous Phenom family used by LIGO and Virgo and so on. So these people have asked the code and they are just using it. Small presentation in the hope that someone gets interested and contribute to this. I'm done. I have some other slides, but I will put them online, and there are links. These are links to the highlights and the papers that you can check if you are interested. Thank you.
So great, thanks, Sebastiano. I think this is very interesting for the community. I would suggest to move the discussion to Slack. I posted hashtag showcases channel. I created one. We can discuss this further. Also, the link on the website isn't working to the slides. I will correct it as soon as possible. So next, so thanks again, Seba. And next we should have Wenbiao Han. Is he present here? Is he able to? Because we've had some time zone confusion. So Wenbiao Han, are you ready to present? He's here in the Zoom call. Okay, so it seems not. So next would be Simone Albanesi. Simone, are you here? Yes. Okay. Great. So Simone will tell us about gravitational wave fluxes from a test particle on eccentric equatorial orbits around the black hole, comparing EOB and numerical results. Please, can you share your screen? So we see your screen, Simone. We don't hear you so far. You have to turn on your microphone.
Okay, are you hearing me now?
Yes.
Okay, perfect. I'm Simone Albanesi from the University of Turin, and I'm working on eccentric orbit on equatorial plane of Kerr black hole with Naga, Caramello, and Bernuzzi. I'm going to show some analytical results obtained with an eccentric EOB model and compare these results with numerical data from Theo. The dynamic is generated by solving Hamilton's equations using the standard EOB Hamiltonian. Since we use test particle, these are reduced to the Kerr Hamiltonian, and we are not using any radiation reaction, so we are talking about geodesic motion. The waveform is calculated in the EOB model by taking the product of these two factors. The first one, the Newtonian, can be calculated by taking derivatives, so source multiple moments, while the second one includes the post-Newtonian information but resummed. In the current models, we take the derivative of frequency and radius and put them equal to 0 because we're studying circular orbits. But if we switch on eccentricity, we can't do this anymore. So we have to take into account also these terms. We can do this for the leading order, plug the waveform in the angular momentum formula at infinity, And we can factorize the Newtonian circular factor and get this formula. This formula contains non-circular correction that are disturbed is equal to 1 in the case we are on circular orbits and reduce exactly to the angular radiation reaction in the Theo BRSM model. Another way of calculating the flux is to take all these waveforms, the generic waveform, and put them into the angular momentum formula. I'm going to show now some comparisons with numerical data. We can see that in the Schwarzschild case, in very strong field near the separatics, we have a very good agreement with numerical data, even with moderate eccentricity. Now, this is a zoom wheel orbit. This means that we have some circular orbits around the periastron. So this is not really eccentric. So we can move further from the center black hole and see what happens. So for a small eccentricity, but with a moderate spin, we can see that there is always a good agreement for both analytical fluxes. And the agreement is good, at least at periastron, also with very high eccentricity, but only for retrograde orbits, and I explain later why. Now I'm going to show some comparisons with post-Newtonian results. Sorry. This calculation has been pushed up to 9 PN, but here I may consider only up to 6 PN, and that for a generic orbit, bound orbit. And we see that when we are very far from the source and with small eccentricity, the post-Newtonian theory gives a wrong result, but at least converges, while our model, Newtonian prefactor, is in very good agreement with numerical data. And when we go to stronger fields, we see that the Newtonian prefactor is still in good agreement with numerical data, while the post-Newtonian theory has oscillations. This is not a surprise, because we already know that the post-Newtonian theory is varied with small velocity and large distances between bodies. But I'm showing this because I want to stress out that a very important step when we include post-Newtonian information in our model is to take a resummation. And the resummation scheme is a very important step that one has to do. Last but not least, I want to show what happens when we switch on the spin for prograde orbits. So very high spin and very high eccentricity. In this case, at periastron, when the particle escapes from the world, we can see that there are quasi-normal excitations, and these excitations are called wiggles. Now this is a very high eccentricity, so we can see that even for a smaller eccentricity, there are these effects. So this is particularly proposed because we know that the eccentricity of EMRIs will go up to 0.7, but already at 0.5 we see these effects. Finally, I want to show that for retrograde orbits, these effects are negligible. In fact, even for very high eccentricity, there are no effects of wiggles. I hope that this result will be interesting, maybe useful, and that's all. Thanks for watching.
Okay, great. Very, very impressive results, I would say. So thank you, Simone. We can again move the discussion to Slack, and please do so. Next one on the list should be Adrien Druart. Adrien, are you here?
I'm there. I just share my screen. Okay. Does it work?
Yeah, it works. Great. So
okay. So thank you. Hello, everybody. I'm Adrien. I'm a PhD student in Brussels with Geoffrey Compare. And I just wanted to talk to you about a project that we started a few weeks ago. So we do not have any result, just a projection of what we are planning to do. And in fact, what we are planning to do is just to build the C++ class, enabling us to compute waveform fluxes radiated at infinity in the horizon and so on, from emitted for sources located on the horizon geodesics around quasi-extremally spinning black holes. So for sources in neck or near neck geometries, and we want to treat the case of inclined geodesics. So we are interested in such black holes because you have enhanced symmetries in the near horizon region. So you have more analytical control on what you are doing. And also you've got simpler radial expressions. Also, even if those objects are not likely astrophysical, you've got unique signatures in waveform due to the high spin. And those results could be later useful if you want, for example, to study the transition from inspiral to plunge around such black hole. And the state of the art is that now we have a complete classification and complete analytical solution of geodesics, since in near horizon geometries and in the literature there are also waveform for generic equatorial geodesics, and what we want is to move to the case of non-equatorial geodesics. And I cannot change my slide. What's okay. And so what the main tool we want to use to dramatically simplify our computation is that when you're dealing with near horizon geodesics, in fact, you can relate any generic geodesic to a spherical geodesic through an appropriate change of coordinate that's called the conformal transformation. And if you know the waveform or the flux radiated on your spherical trajectory, you can construct back quite easily the waveform on your random, for example, plunging geodesic. And so the core of what we plan to do is to compute the solution to the Teukolsky equation for spherical geodesics. So we get the waveform for spherical geodesics. And we plan to do this decomposing the solution using fundamental frequencies of the geodesics and action angle formalism and so on. So the solution to the Teukolsky equation turns out to be simply a sum of modes over some modes that I called here FLMK. And if you are able to compute somehow efficiently those modes, you have access to the waveform and the flux of your spherical trajectory. But through this quantity, you have also almost direct access to fluxes and waveform for any geodesics in your near horizon geometry. So the main goal of this project will be really to implement the computation of those FLMK, those sorts of Fourier mode in your resolution of your Teukolsky equation. And the form that we plan for this project will be to build the C++ class, which is quite user-friendly. So you could define a trajectory with a bunches of parameters and then ask the code for computing whatever you want related to this orbit, for example, geodesics parametrization or your fluxes or your waveforms. We want this to be supported for generic near horizon geodesics. And if it's possible, we want to use Ball arithmetic to be able to reach arbitrary precision, for example. We begin the implementation, but I'm not really used to numerical stuff, so it's a little new and it's really the beginning. We used already some tools from the black hole perturbation toolkit, for example, the implementation of spins weighted spheroidal harmonics that's contained in Gremlin. And of course, there are a lot of open questions. So the main one will be to find an efficient way to compute those FLMK. And so it's really useful to learn so much from all your talk and to see what you have already done. And I'm really hoping that this workshop will give us idea and insight for the future of this project. So if you have suggestions or so on, you are warmly welcomed. And thanks for hearing. That's all.
Okay, great. Thanks a lot, Adrien. Thanks for showing us your work. We can discuss on Slack again. So,
thank you.
Very nice. Next on the list, we have Viktor Skoupý. Viktor, are you with us? Hi. So we don't hear you, Viktor, at this point. Do you have your microphone on? Okay. In case there is an issue with the microphone, yeah, so in case there is an issue, maybe we can go to the next talk and you talk in 5 minutes after you solve your issues. Okay. Okay, so next one should be Gabriele Andres Piovano.
Hi, I'm here. Can you hear me?
We can hear you almost too well. And,
yeah, maybe I should have to set the microphone. Okay, let me share the screen. Okay, let's see. Can you see the screen?
So we can see the screen. Thank you. So please start your.
Okay. Hi, I'm Gabriele Piovano. I'm a PhD student in the gravitational physics group in Rome. I don't have a presentation, so I will just show the notebook which I'm working on in a moment. I'm working on EMRIs, in particular on EMRIs with a spinning secondary, and using the spinning of a secondary is an important piece to add to the modeling waveform because it enters at the phase at the same level at the first order correction to the self-force. I worked in a previous project on calculating the fluxes in a simple case of a circular orbit on the equatorial plane with the spin of a secondary aligned to the axis of a primary black hole. And what I'm doing now is to try to see if one can measure the spin of a secondary and with which accuracy we can spin the spin of a secondary still in a very simple case. So in this notebook, I'm just playing around with the waveforms, and it's an early stage of development. So here I have, I'm just loading all the data that I calculated previously. Here I have calculated the spheroidal harmonics using the package of the black hole perturbation toolkit, even if not a very fancy way. And at the end, I linearize everything in the spin. And then I interpolate everything in R. And then I don't know if you can see here. I'm doing the evolution of the radial orbit for using some fluxes for some values of the spin, and I plug in the evolution in the phase, and at the end I put everything together in the function. We calculate the waveform, and here I linearize in the amplitudes in the phase, still not in the orbital phase. Here also linearize in the angular part. And just one last thing that I want to show you. Okay, it's here that I plotted the waveforms for a case with a spinning secondary for a case with a secondary with no spin, and for a secondary with spin, and for a spin of a primary 0.8, spin of a secondary 0.8 in one case and 0 in another case, and for this time interval the overlap for the plus polarization, here for the cross. And when one moves later in the spiral, one can see with naked eye that they are out of phase. Sorry? I don't know if you can, maybe I misheard. Just showing one last slide here. They are completely out of phase near the end of the spiral. And that's pretty much it.
Cool, great. Very nice notebook. thanks you for letting us see what you have worked on, and thank you for letting us see your code. So I think we should cut a little bit into the coffee break with at least one more presentation. So is Viktor already, is his microphone working maybe?
Can you hear me now?
Yes, now we can hear you very well.
Okay, so I will share my screen.
So I think Gabriele has to stop sharing his screen first. Okay, great.
Okay.
So usually you should share your entire screen. That's the best thing. And I'm just going to read the title of your talk. Gravitational wave fluxes from spinning test body orbiting your black hole.
Yes, can you see my screen now?
You can see your screen. Maybe you can make the slides a little bit larger. So that... yeah, okay, great.
Okay, so hello, my name is Viktor Skoupý, and I'm a PhD student of Georgios Gerakopoulos at the Astronomical Institute at the Czech Academy of Sciences. And the topic of my thesis is gravitational wave templates from extreme mass ratio in spirals. We are using time domain code, the 2 code, and it generates waveforms and energy and angular momentum fluxes. And our goal is to improve it for generic, eccentric, and off-equatorial trajectories of spinning particles. The time domain code is tested on circular equatorial orbits. I have written a frequency domain code to compute energy fluxes from circular equatorial orbits of spinning particles to compare it with the results of the time domain code. The energy flux can be computed from the radial function and its first and second, and for spinning particle third derivative, and some coefficients I derived using Mathematica. Now I am going to show you my code. So here I used the Teukolsky package. First I defined this function which returns parameters of circular equatorial orbit on some radius r0 and with primary and secondary spin. And then I defined this function which calculates the energy flux of a mode with angular and azimuthal numbers L and M from some orbit. I used these functions from the toolkit, spin-weighted spheroidal eigenvalue and spin-weighted spheroidal harmonic S on the equator, and Teukolsky radial, its value on the radius r0 and its first derivative, and both the solutions for the flux to infinity and for the flux to the horizon. And these are the coefficients, and these are the formulas for the fluxes. I used the results to find the accuracy of the time domain code. For example, here on this plot is relative error of the time domain code for different azimuthal numbers M. Or I use it to find how many terms, how many modes must be summed to achieve some accuracy. Recently, this paper by Piovano et al. Was independently published, which deals with the same thing, and I compared results of my code with the results of in this paper, and they agree. Okay, thank you.
Okay, great. Thanks, Viktor, for showing us your code once again. So This was a really great session. We saw. So we have another session after the coffee break where you will have showcases, and I just want to show you what is. So what is what? Okay, so hello everyone. Welcome back from the coffee break, the virtual coffee break. We have Chris here. Chris, to start with, can you just tell me how to pronounce your surname correctly?
Munna.
Munna. Okay, great. So maybe I mispronounced it previously.
It's fine. It does.
It's so Chris is going to tell us about a PostNewtonianSelfForce package in the black hole perturbation toolkit. So please, Chris.
Okay, can you see my screen? Okay, let me make this full screen.
Maybe a little bit larger the font. It's a little bit tiny.
Shoot, let me. Oh no.
So if you just press Control and scroll, it would. Or yeah, this would also work.
The zoom is not showing up for me. The option is grayed out.
Magnification.
Okay, here we go. There we go. Better?
Great.
Okay. All right. So like you said, I'm Chris Munna, and today I'm going to be talking a little bit about the PostNewtonianSelfForce package on the toolkit. For the most part, it's relatively straightforward. So I expect that this talk shouldn't take a ton of time. I'm going to just go over some of the series and then go step by step through one of the series, which is the eccentric energy flux for Schwarzschild at infinity, which I think covers most of the functionality of the package. And then at the end, I have a few practice questions I'm going to give everyone a little time to work on, and then I'll go through a slightly more complicated example. So first, a little background. Oh yeah, and the last thing is most of what I'm going to present today is already on the toolkit in the examples and tutorials package. I added a little bit at the beginning and end, a little broader introduction and a little bit of practice. And if anyone is interested in getting this extra portion, I can put this full notebook on the toolkit or send it out as well. So the PostNewtonianSelfForce, as the name implies, it's about. Is there a way I can turn off this notification? I'm just going to go with it. Okay. As the name implies, it's about taking first order black hole perturbation theory quantities into the post-Newtonian regime and then obtaining post-Newtonian expansions to approximate those quantities. And really, I should just say first order black hole perturbation theory now, because as soon as the second order formalism is developed or is continued to be developed, then we'll be able to post-Newtonian expand those as well. So how does this work? We find small post-Newtonian parameters and expand the black hole perturbation theory formalisms in them. Some common choices are 1 over p, where p is the semilattice rectum. It can be expressed in terms of the smallest and largest radii of the orbit for a bound orbit, like so. V for some characteristic velocity is also commonly used. In many cases, it's just given this definition, but sometimes authors will use more complicated definitions. Y is a very frequent choice because it's gauge invariant. It's related to the azimuthal frequency, like so. These are all very common post-Newtonian parameters. And then at each order in the post-Newtonian expansion, you can have other expansions as well. And so one frequent appearance is the Darwin eccentricity E. So at each p in order, you'll have an expansion in E for eccentric orbits. And then you can also have this spin parameter Q, which is related to the spin of the black hole A over M to make it dimensionless. Some expansions will be, for some p in series, you'll have an expansion in Q, and others they'll be exact in Q. And so as an example, a few examples of series that exist on the toolkit. I just listed a few out here. So you can use this function post-Newtonian expansion and then describe the file name or just describe the series you're looking for. If you run into a naming conflict, you can add strings to exclude using this exclamation point out front. And so we have the energy, the flux at infinity, the flux at the horizon, circular and eccentric, redshift, the redshift invariant, which is in the conservative sector, a local gauge invariant quantity, depending on the metric perturbations at the location of the particle. Spin precession invariant, another local quantity, tidal invariant as well. So this is the kind of straightforward way to get these expansions. If you want to go for a slightly more awkward approach, you can also load them this way. And if you run into trouble, sometimes this method can bail you out. So once you have the series loaded, you can get information about them. And so just an example, you can get the name and the description. So here's a brief description of what each of those is. For the fluxes and the invariants and so on. And so yeah, so that's a basic introduction. So now I'm gonna go into a little more detail about the functionality and by working with some specific series in the energy flux at infinity for Schwarzschild eccentric orbit in spirals. So once the package is loaded and it's on your Mathematicus file path, then you can load it like so. So the energy at infinity, Schwarzschild eccentric, flux, and infinity. Here's a slightly larger list of pieces of information you can get. And so this is something that I worked on with collaborators at UNC. So that's all there is there. Once you have the post-Newtonian expansion loaded, you can get the full series. And so if you just do this command series, it'll give you every piece of information in the series. And then in most cases, that's going to be an extremely large series. It's not going to output all of it, and it will be a little difficult to work with. So there are a bunch of methods on the toolkit to kind of narrow down your focus. The easiest way is to just take the series and truncate it at a certain order. And so here I've truncated it at 3pn relative order by introducing this, this truncation term. And so if you look here through, you can see the 0pn, this is the Peters-Matthews term, 1pn, the 1.5pn term is given as this special function, and I'll go over that in a second, 2pn, 2.5pn, and 3pn. From here, you can narrow your focus down even more by instead using this post-Newtonian coefficient function. You take your post-Newtonian expansion, and from that you use post-Newtonian coefficient. And so as an example, here's the 0pn Peters-Matthews. It appears at 5pn absolute order, or y to the 5th absolute order, but 0pn relative order. And so this is kind of a shorthand for this second line, so they give you the same thing. Some other terms in the post-Newtonian expansion have closed forms. And so these are two more examples. The 1pn term, this is a closed form. This is exact to all orders and eccentricity. And this is the 6pn log squared term, also exact. Once you have these terms, it's fairly straightforward to get numeric values and numeric approximations. You can use the in Mathematica function. So those are closed form functions or post-Newtonian terms, but many of them are not. Most of them are not. And these come in a couple different varieties. For the most part, what we have is a singular factor and then multiplied by a series, which is expanded to some finite order. And these are saved using the resum series data functionality. To find out how that works, you can look into the resum series file. So as an example, here's the 6.5pn log term. You'll have the singular factor, the divergence is e goes to 1 multiplied by this series. And so the way it's saved, you can extract the singular factor and the series separately. So once you have this term saved, you go in and you can extract the series data to get the series here, and then the singular factor to get the singular factor. If you don't want the series all the way to e to the 30th, which is as far as it's given in the toolkit, then you can truncate it to a lower order, both with or without the singular factor. So if you just do it like this, then it'll expand out the singular factor and give you what you have here. On the other hand, if you take the series data portion, then it'll just truncate this attached series. On the other hand, the extra functions are handled a little differently. So if you look at the 1.5pn term, it's just given as this here. What you do is you just take the function that you see here and plug in something for this highest power, and it'll expand it to that order. And this is kind of or there's an equivalent method that will expand it to the same order. And that's if you just take the post-Newtonian coefficient and then substitute in the highest power and then release the hold that was placed on this function to prevent it from evaluating at the beginning. And then similarly, this is also saved using resum series data. So you can extract the series itself by doing the series data. Numeric approximations are obtained easily enough using the normal function. And then substitution, you can see the impact of the singular factor when you go to high eccentricity or eccentricity approaching 1. So if you take with the singular factor included, you get a very large number. But on the other hand, if you just take the series that converges, then you find a much more reasonable answer. The 3pn non-log term has this special function, which is a step more complex than this 1.5pn function, this chi function. So here's the full 3pn energy flux. And so let's take a look at this chi 3pn function. If you place a particular order in the arguments, what you'll get is you'll get this first thing, and then you'll get this series expanded to this order. And so the series here converges, but the rest of this represents the divergent behavior of this chi 3pn function. So this first portion is a logarithmic divergence, and then here you have an algebraic divergence, but then this last portion converges. And so if you want to just recover this last portion, what you actually need to do is subtract off this negative portion, and then use series data. So this portion is saved with the resum series data functionality. And so what you get is the convergent series portion expanded to higher order. Okay. So I have in the tutorial notebook on the toolkit, there's pretty much an exact replica of this for the angular momentum flux at affinity. But let's just move on to a few basic exercises and then a quick example. And then, as I mentioned, this is relatively short, so then I'll be done. So to start, I'm going to just leave these questions up for a few minutes and give everyone a chance to work on them. They're pretty straightforward, just to get your feet wet with handling these things on the toolkit. So I'm going to give everyone a few minutes, and then I'll go through them. And then we'll go through this last example. And while y'all are doing that, I see a question in the chat. So can you go up to arbitrary order in the series expansions, or are there some limitations? And so sometimes yes, sometimes no. The functions that are loaded as special functions, like the 1.5pn term, those can go up to arbitrary order. However, other terms using the resum series data function, like that 6.5pn log term I showed, that one is limited to e to the 30th, which is what was shown in the tutorial. That's as far as we found it, and that's as far as it is on the toolkit. So you can't go beyond that order, even though the expansion does continue beyond e to the 30th. Good question. Okay, let me go over this first question, and then I'll give you a little more time for the next two. And so basically, here's how you do it. Go into the eccentric orbit, get the redshift invariant. I'm asked for 1/p⁴ relative order, so we're going to use the not y file, the one that's given in terms of 1/p. And then I asked for relative order, and so it starts at 1/p. And so technically, the 1/p⁴ relative order is 1/p⁵ absolute order. And so from there, you can just go in and find the e⁸ coefficient. Straightforward enough. Okay, and give you a little more time to work on the other two. No, I'll leave this up in case anyone missed that. Okay, let's take a look at the second one. So if you find the chi6pn special function, it's given by this. And so loaded to e⁶ order in this convergence series, you see you have this first portion and then the convergence series. We need to isolate the convergence series. And so then we have the sum of these two in the series data. And so this extracts it to e⁸, but now we're looking for the approximate value that this converges to. So we do this substitution or do this summation. And then what I've done here is I've created a pure function that finds the approximate value for e = 1 of this summation. So the convergence series portion to various orders from 10 to 50. And so you can see that for the first few, it converges on a value. And then for the rest of them, it stays at that value. So we can be pretty confident that this is what it converges to as e goes to 1. Okay. And another minute for the last one, then I'll do that one, and then we'll move on to this demonstration. And leave this up for another second. Okay, last one here. So you can load the circular orbit flux, just called infinity in this case, through either method. And so I've given here a way to truncate the series and just kind of what it looks like at low order. Then you can do something a little more complicated. So first we created the pure function in order to vary the order from here to here. Substitute it in. So this part's a little tricky. The expansion is given in y, but you can find out in a couple different ways, including using the Kerr geodesics package that for circular short shield orbits, y is just 1/p. And so approximate it to 15 decimals, create the values here for various PN orders. You can see it's kind of converging. And then to show that it's converging, you can take the differences and find out the residuals, and you see how the residuals dying off as you increase in PN order. And so, you know, P of 10, you're already getting in pretty close. That's pretty good. Okay, leave that up for a sec. And so now and if anyone has any questions on any of those, you can reach out or post in chat, etc. Okay, so let's briefly look at this demonstration. And so for this, I'm going to also use the curve geodesics package. We're going to use the energy and momentum fluxes to describe a Schwarzschild in spiral. And so for that, we need expressions for the energy and angular momentum and the frequency. And so we can get that from the curve geodesics package. And so for Schwarzschild, got A of 0, inclination of 1 here and here. And so this is the expression for the energy for Schwarzschild geodesics and the angular momentum. And then this actually gives Y in terms of P and E exactly. It's a very complicated expression in terms of elliptic integrals. In a lot of cases, what you'll end up doing is expanding Y in terms of P and E to high PN order, but this also works fine for the numeric simulation. So we also need to get, the goal is to basically get P of T and E of T using the post-Newtonian-Selfforce approximations. And so we need P dot and E dot in terms of the energy, change of energy and change of angular momentum. And part of this is most of this is based on a notebook that Niels sent me. So I want to thank Niels for setting some of this up. And so you can, this was also a question I believe that Martin posed yesterday. So hopefully a lot of you got a chance to solve that. And so all you basically do is E dot is equal to dE dP, dP dt plus dE d eccentricity, d eccentricity dt, and so on. And then you can reverse solve to get the change in the semi-lattice rectum and eccentricity in terms of the change in energy and angular momentum. And so that gives you that here. So then we're going to use the post-Newtonian-Selfforce data. So we need to load in the eccentric series, and I've chosen to just truncate it at a relatively low order, 3 PN relative for both, or technically 2.5 PN relative for both. And so this loads the series to the given orders. And so then what I've done is I've taken the series, and to ensure that the special functions are taken care of, I set the highest power number to 80, e to the 80th, and then I release the hold to make sure that those functions are evaluated. And then I kill the series, take normal, and then replace Y with its value in terms of P and E, because we want everything in terms of P and E to evolve the ODEs. Okay, and so here all I do is I substitute in for P and E functions of time in order to use ND-solve, set some initial values for the mass ratio, the initial value of the semi-lattice rectum and of the eccentricity, and then use ND-solve here. And you end up getting these interpolating functions. Mathematica involves it, and it does go pretty quickly. And so then from here, you can use this domain function for from the interpolating function to get how far out the domain goes, and then plot. And so when you do that, you get something like this for P, where it just kind of decreases monotonically. And then for E, you get also this decrease, but then there's a little spike at the end. And partially that is kind of well-known behavior. There's a little spike at the end, but then also partially it's important to realize that the post-Newtonian expansion does break down to an extent as you get in very close. And so obviously you can increase this to higher order in the eccentric fluxes, they currently go up to 8.5 pn and varying orders in eccentricity. And we have more work in the pipeline to hopefully be extending that soon. And so hopefully we'll be able to go to very high order with these. I know Fujita in his paper that takes the circular orbit energy flux up to 21 pn or extremely high order, he found that by going to those very high orders, you could get convergence all the way into the innermost stable circular orbit. And so that makes the high order post-Newtonian series very useful for these kinds of things. And so, yeah, that's pretty much it. I'm open to any questions or comments, or if anyone has anything to add or would like to explain some functionality that I missed, etc. And I see a question to share this version of the notebook, and yes, absolutely. I can either add it to the toolkit or I can send it to Niels or someone who can forward it.
If you send it to Wojciech, he can upload it onto the workshop website.
Okay, even better. We'll do.
Okay, great. I think you have answered all the questions that already appeared in the chats. I haven't checked Slack, but maybe more discussion can happen there. So this was a great overview of the package, and thanks again for giving the talk.
Yeah, no problem.
So we have now finished the PostNewtonianSelfForce talk, and we are actually ahead of schedule. So we are 15 minutes ahead of schedule. I don't know how we should do this now. So
maybe some.
So
I would recommend sticking to the schedule, I think. As in we can wait and take a little break, or people can talk.
Maybe
just
we
in case
could.
anyone's coming.
We have a few extra of the showcase speakers.
That's true.
So for instance, we are keeping Wenbiao up, even though it's after midnight for him, which I did not realize when I just made him forward. So I don't know if Wenbiao is listening right now.
I'm here right now, so mean that I can talk now?
So if you want to present now, it's.
Oh yeah, okay, no problem. I can do now. Yeah, perfect. Yeah.
Perfect.
Share the screen. Okay, can you see my screen?
Yes, that's great.
Okay. So now it's fine?
Yeah, great.
Okay, so I will introduce a little bit about our EOB and Teukolsky codes for the EMRI, and also another one we call XSPEG for the EMRI with the arbitrary axisymmetric black hole. So, and this is the EOB Teukolsky code, but right in Fortran. And we have set the initial data about and the parameters for the mass of the system and the spin, the effective spin of this EOB system, and the mass ratio and the same letters and extrinsic. Then we put in the EOB dynamics and get the orbital frequency to the first domain, the Teukolsky equation, and so solve the Teukolsky equation in the first domain and get the waveforms and fluxes. And use these fluxes, we go back to the Teukolsky, go back to the EOB dynamics and evolving the orbit. And also we have Teukolsky codes in the time domain. So we have the source term and then take it into the Teukolsky code in time domain, and also we can solve the waveforms. For the radiation reaction, that actually we use you can use the Teukolsky fluxes, but sometimes we for the accelerate the evolution, we use some in support some function to simulate the Teukolsky flux, and so you can accelerate your code and calculate the waveform very fast. Okay, and this is UV dynamics for the scalar orbits, and you can see that we have a Hamiltonian, and then you get the r dot phi dot pr dot p phi dot, and the p phi dot connect to the flux and angular momentum flux. And also we have a radiation reaction on the r direction and radial direction. The angular momentum fluxes is getting calculated from the Teukolsky equation. So this is a Hamiltonian. You can see okay. Hamiltonian. We have the H effective equals to H no spinning part and spinning part and plus some the S star. S star is the effective spin of the effective test particle, in the UV system. Okay. Also, we extended to the eccentric orbits, and we calculate the frequency orbit fundamental frequency of the UV dynamics analytically. So it's so we can get the frequency of the r direction, radial direction, and also the phi direction very accurately by calculating this these two integrals, and we present the r in the radial coordinates in with another another parameter chi here. You can see how to put my yeah. I don't know how to release my mouse. I don't have a pointer to this equation. Okay, so then we can transfer this transfer the original UV equation to the below two equations, phi dot and r dot, and then we can calculate the eccentric orbits with the frequency and also the orbital evolution very fast and accurate, and take this to the Teukolsky equation, and then finally we get the waveforms and energy fluxes. So this is for the a case, just a case to show an example to show the result of our code. Okay, but here actually we don't have the omega theta. We don't have the omega theta not yet. So but we are working on this to try to make our code also working on the inclined orbits. Okay, this is for the, okay, also we have for, sorry, this is some with Chinese, we have a time domain code, but now it's only working on the circular orbits, but sometimes, of course, the radial orbits is, some simple orbits is also, it works. So to calculate the inspire and merge. And the second part is we want to introduce a little bit about the XSPEC. This code is working, is writing in the Python and the C++, and this is for the EMRI waveform with arbitrary metric black hole, and the metric we use is KRZ metric I will show later, and we have some these files in these codes. We have an in-car file what you can input your parameters of this system, the Mars spin and the something, you know, the some meters and the distance from Mars and the directions, and then the out file will in the wave car and out car, and also within the package is source file of this code. Okay, and this is the parameter input format, and you can see you can input the mass and mass ratio, spin, eccentricity, and the inclination angle, and also the, you know, here the metric. You can see that we have some different parameters value. Now he's put 0, 0, 0, but you can use other numbers, for example, 0.1, 0.1, 0.9. This means that the derivation from the car black hole. Okay, so this is from the KRZ metric. I think I should have here. You can see that we have the this metric, KRZ metric. You can see that we have the in the n square. You have delta 1 and delta maybe delta 2 also here, and in the B faction you have delta 4, delta 5, something like this. Okay, so if you put this number here, but now in this code only have three delta 1, delta 2, and delta 3. But now we are, you know, put all the delta here from delta 1 to delta 6 and or to delta 8, or put in the new code. It will be updated soon. Okay, so the orbit evolution is calculated from this equation, and we get the to calculate the radiation reaction force from the energy flux and angular momentum flux and the cut and the flux of the cut constants. So okay, this is waveforms and orbit evolution for the car black hole and the KRZ black hole, and you can see the little difference if you look at it in details. You can see the waveform, two waveforms are a little different. So these are two black holes with the same mass and but different spin and different inclination angle, and you can see that is two waveforms here. Okay, this is my show. Thank you.
Okay, great. Thank you, Wenbiao. I don't see any questions here in the chat window, but still there is the Slack space which we have set up for this workshop, and hashtag showcases is the channel where you can discuss. So Leo's question. So Leo has a question. I think I missed something. Where do the fluxes come from for the non-Kerr spacetime? So I assume that's comparable mass case, or?
Sorry?
I'm not sure.
Excuse me? You mean for the?
Oh, yeah, right, probably this.
Yeah, the local space-time is all in this metric. Then we use some parameters delta 1 to delta 8 to to represent all the deviation from the Kerr black hole.
So the question of Leo is, how do you compute the?
So I didn't see the question. Where is I can see the question? I'm sorry, just here I have to find. Maybe I should. Oh, here. Sorry. Oh, where does the flex? Okay, this flex we use just the post-Newtonian one.
Okay. Okay, great. So thanks a lot for even though we had some misunderstanding about the time zone, it's great that you found the time to still talk to us and show us your work.
Was asking about Postnewtonian 1.
And so Alessandro Nagar has Postnewtonian 1. Well, okay. Maybe we can move the rest of the discussion to the chat or to Slack. And we have about 4 minutes until the next talk. So I suggest we have a very short break, and then Niels will start on time in 4 minutes. Okay, so welcome back, everyone. We now have the talk of Niels Warburton about the Gremlin package in the black hole perturbation toolkit.
Great, thank you very much. Yep, so obviously Scott Hughes was meant to give this talk as he's been the main developer of this code over many years. Unfortunately, he had to drop out at the last minute, so I'm going to do my best to talk about the code and give some examples because I used it a fair amount when I was working with him before and when adding it to the toolkit. So the first question that might come up is, why is it called Gremlin? Slightly odd name. And actually, we tried to release this package. After Scott changed the package to having MST in it, he renamed it to Spectre some years ago before it was publicly available. And we went ahead to release it. And of course, as we did, we were reminded that the spec code recently has had a new rewrite, which is now called Spectre. And so they beat us to it in terms of a publicly named piece of Gravity code called Spectre. And so Scott reverted to the original name that he'd used when he started developing this code way back in 1998. And that name was Gremlin, which stands for the gravitational radiation in the extreme mass ratio limit. But because Gremlim doesn't sound very good, he changed the M to an N. And we got Gremlin. So that's the code I will talk about today. So what is this code? Well, it is a C++, you should think of it as a C++ set of classes for solving the S equals -2 Teukolsky equation in the frequency domain, particularly when you have a point particle source, as there's a lot of useful functions for point particles. So in that sense, it's very similar to stuff we've seen earlier today from talks from Leanne and Barry about MST and the Teukolsky code that's in the toolkit and the Mathematica side of things, but in C++. So that gives it, in general, the advantage that it is much faster, and so great for exploring parameter spaces. But its disadvantage, of course, is it's actually hard-coded to spin weight -2. This is because this code grew out of solving the Sasaki-Nakamura equation, which is generally written down specifically for -2. If you want more generic spin weights, you can use the Mathematica packages. And it's also obviously, as you might imagine, restricted to machine precision, although internally it does actually use some extended precision for some parts of the calculation. So Gremlin, as it says here, also contains a set of executables, which I'll talk about and show. Those executables are kind of a collection of things that Scott has looked at over the years. A few of them are more useful than others, depending on what you're interested in. So I'll just mention a few of those, but you're free to look at the other ones, and they are lightly documented as well. So Gremlin itself is actually a very generic piece of code. It's the stuff you've seen from the papers of sort of Drasko and Hughes in 2005, which can solve for gravitational waves from fully generic bound orbits in Kerr spacetime. So arbitrary eccentricity, arbitrary inclination, and whatever size of orbit you like outside the separatrix. In general, it will compute that for a Swirl harmonic index, and then for indices M, N, and K, which are the modic indexes, so the overtone numbers for the azimuthal, the theta, and the radial motion. And then it stores a bunch of useful properties that you might care about. So property of the orbit, obviously the amplitudes, that then you can compute the fluxes, and at the moment it's storing some pieces of the radial solution at the particle itself, though not enough as you might need to do the self-force. That's a very generic code, but for various reasons, that's not yet releasable. And the main reason being that it currently uses some proprietary libraries. It still has some numerical recipes code in it that has to be extracted before it can be put into the toolkit formally. But it has been a working research tool for Scott and his collaborators for a long time, so it's pretty stable. It's well understood, but it still needs to be tidied up. One of the things that we did with the currently released version in terms of tidying this up is we made it so that it outputted data in a kind of a very generic format. It uses HDF5 files now, which is a shareable and easy to read format, whereas the old version of the code would just dump binary files, which you couldn't move from machine to machine. So as it says on this slide, the cleanup is currently underway, and we hope to have the generic version of the code available in the toolkit in the coming months. But it just depends on having time to tidy that up. But Scott is open to sharing it privately, and he has done so in many cases. So if you are interested in getting access to that code before it hits the toolkit, then you perhaps shoot him an email and he can discuss that with you about how to share it and how to use it. In the meantime, what Scott has released is a kind of subversion of it, which only does the circular equatorial orbits. And in this case, instead of solving for P and X, you just solve for some orbital radius with some flag, whether or not you're going prograde or retrograde. And the frequency spectrum just drops down to being m integer m times the azimuthal frequency. And this code for the meantime is called Gremlin EQ, and that's the one that you download from the Black Hole Perturbation Toolkit. Okay, so hopefully, if you want to kind of follow on in this little talk and this tutorial, you've already done this, but if you haven't and want to try quickly, then the installation roughly works as follows. You should download it via the Git repository from the toolkit. In order to install it, it needs some libraries that are pretty standard, but if you don't have them, you'll need to get those. There's some instructions on the Slack about if you're using apt for Linux, or if you're using brew and Mac, about what you need to do to install these libraries. So you need the GNU Scientific Library, the GSL. As I said, the code actually uses multi-precision inside its internal workings. That's because it uses MST, and MST uses high precision, as we kind of saw earlier in the day in Barry's talk. It also needs FFTW, Fourier transform library, and it, as I said, outputs data in the HDF5 format, so you need to install that library as well. These are all freely available, so it should be straightforward to install if you haven't already. Of course, you'll need a C++ compiler. We've tested it with the GCC G++ compiler, and then you compile using make. And it's pretty quick. It takes about a minute or less than a minute, maybe in 20 seconds on my computer. So once you do that, it will compile a bunch of code, and then it'll put us into a subdirectory called bin for binary, a bunch of useful binaries. And I'll just look at a few today and show you some examples how you can compute things and then extract that data. And I'll do that in Python and in Mathematica as well if there's time. So probably the most useful one is just a little binary called circeq for circular orbits in the equatorial plane. And if you type /circeq with no arguments, that'll then tell you what arguments you need to supply. So you get the radius, the spin of the black hole. The third argument should be 1 or 0, depending if you're prograde or retrograde orbits you're interested in. And then the LM mode you want to compute, and then finally the output file base name. So it'll give the file we named that name plus .h5. It's an HDF5 file. You can then, once you have that, you can use fluxes to extract the fluxes from that file. And I'll also talk about another little, oops, I don't know to quite update the slides, but this should be /GW, which is gravitational wave, and it will compute the snapshot waveform for that particular set of modes that you computed. So I'll show that in a moment. Just to finish, as I said, on the slides, internally, the code is using the MST method to solve the radial equation, and it's using basically the spherical expansion method that we saw in the talk I gave yesterday to solve the angular equation. In terms of things for tomorrow, if anyone's interested in kind of hacking or adding things to Gremlin, one thing that would be really great to have would be Python bindings. So a lot of people now use Python, and it'd be really great to just access all of these internal kind of classes and make calculations kind of by locking the C++ code into Python some way. So if people are experts in that, we'd love to hear from you, and that'd be a great thing to add. Currently, the code just computes fluxes. And in fact, the birth of the toolkit basically came about while I was at MIT. There was sort of frustration that his code sometimes would fail for certain modes to not have enough precision to compute self-forces. And so we'd like to kind of push that and actually go ahead and add self-force calculation, so calculation of local invariance to the code. I certainly have got bits and pieces of that for at least the redshift invariant. Also, there's been a lot of you I've seen have been looking at spinning secondaries, and you've made great use of the Teukolsky package. One thing you could do quite easily, because this code already computes the radial solutions, you've just got a different source that could be added quite easily into this Gremlin code, and then we could extend Gremlin to compute spinning secondaries. And as I said, it's much faster than running the Teukolsky code because it runs in C++, and it's very easy to parallelize across many machines. Okay, so that's the end of the talk, or the end of the slides. Let's try and set up my screen so I can share multiple windows. So I was going to try and use Zoom as a share portion of screen. So let's see how well this works. So I was going to try and share because I want to have a terminal open. So let's close that. We don't need that anymore. Okay. So hopefully now you can just see a portion of my screen. You don't need to see yourselves. Okay, so as I said, if you go ahead and download the code, make this as big as possible. Is that reasonably reasonable? readable?
Yes.
Blue's a little faint, but you should be able to see what's going on. So here I'm on my machine. I've installed this in a. I keep all the stuff for backup automation toolkit in a directory, and then a subscript, subdirectory called Gremlin. And when you download it, you'll get a bunch of these files, and then you can just type make to compile it, assuming you've got all of the relevant libraries installed. One thing to note, if you do get errors, you might need to look in the make file, and there's a bunch of paths you might need to set if you end up installing the GSL or HDF5 in some non-standard location, and you can just set those, and that hopefully would allow it to be found in the compilation. Okay, but once you've done make and you compiled it, you should be able to go into the binary directory, and you'll see this whole. Actually, before we do that, let's talk about documentation. So there's in /doc, you'll find documentation, and in particular, if you open doc.pdf, you will find a PDF written by Scott, which gives details of the inner workings of the code. So let's make that a little bigger. So this was written by Scott just before actually the last toolkit meeting we had last year at MIT. Some details about installing it and about how the package got its name and contributors over the years. If you're interested, then there's a whole bunch of classes that Scott briefly describes. He likes to name things with sort of acronyms. So you get an SWSH class for spin-weighted toroidal harmonics. So if you're looking to compute harmonics, that's what you would use. And I heard earlier today someone had been doing that using the Gremlin code. So that's what they would have extracted. FT is basically the MST methods, named after some early papers by Fujita and Tagoshi. There are classes to do with computing geodesics, so ending in G here, so circular equatorial Kerr geodesic. Classes do computing the radiation reaction. So you'll find it then. And this final one, CETD, is a driver that sort of adds all these things together and computes various things and outputs an HDF5 file. What's most useful about 2.5 is it lists the actual format of the data is outputted inside those HDF5 files. So we'll look at that in a moment. But this is what I reference when I was building the little notebook I'll show you. So these are grouped into, basically you'll see is you compute data for each mode, and then each mode then has 19 bits of data, which you might find useful. So these can be things like the harmonic, these can be the real imaginary parts of the complex amplitude infinity, complex amplitude at the horizon. Also contains the radial solutions of the Teukolsky equation at the particle itself, as long as it's radial derivative, both the in and the up solutions. It stores the fluxes to infinity and through the horizon, both for the energy and angular momentum. It also nicely pre-computes the R dot, basically, resulting from the infinity flux, and R dot resulting from the horizon flux. And then there's some other classes, and you can see, and if you're digging into code, that's where you want to look. Some of these, like class title H, would literally stuff that Scott wrote for a single paper. In this case, his work with Stephen O'Sullivan to compute how the Teukolsky solutions perturb the horizon. So that's very specialized, but you might find it useful. And then he gives a list of all the different executables. And as I said, you can play around with these, but I'm just going to look at a couple of those now. So let's have a look at those. Before I do that, though, I should say there is another set of documentation. Do I have that open? Here. So again, if you go onto the toolkit website, to the Gremlin webpage, you will see, oops, the wrong thing there. You can go on documentation, you can click documentation page. Is my screen still updating?
Yes.
It is, okay. There's a funny thing saying my screen sharing is paused, but I don't know what that means. So yeah, this shows you the documentation. This is just generated using Doxygen, which is run every time the toolkit, sorry, the software is updated. There's an automatic script that reruns Doxygen and puts this on the web page. And again, you can kind of read some basic information about the different classes that are available inside the toolkit. It's pretty light documentation at the moment, but you might find that useful as you're looking through stuff and trying to make stuff work. Okay, great. What about actually using the code then? So on the website, so Wojciech has uploaded some notebooks I sent him, and you can follow along if you like, both in Python and Mathematica. So if you go into /bin, you'll find this circular equatorial orbit piece of code. And you can see, as I said before, it needs 6 different arguments. So let's look at an example. We'll do a calculation for radius of r of 10, spin of 0.9. We'll do a prograde orbit. So we set the third argument to 1 and not 0, which would be retrograde. And let's compute our favorite, the 2-2 mode. And we'll call this R10 a 0.9. So we go ahead and run that. It spits out some information. But you'll see that we've now created a file called R10 a 0.9.h5. And so that will contain all the information that we talked about before. And I'll show you that in a moment. So one thing to note, you can add extra modes. So if you add the 3.3 mode, for instance, and just run it, it hasn't created a new file. It's just added that into the HDF5 file that you see there. The code also stops you trying to do something silly. So if you try and add, okay, I want to create the 4.4 mode, I'm going to do it for a spin of 0.8 rather than 0.9, but I want to add it into that same file, it'll complain and say, I've checked the parameters in that file, they don't match, and so I don't want to add modes of different parameters into the same file, and so it'll stop you doing that. Okay, so that's how you would create a file containing all that data, but how would you go about reading it or accessing it? So first of all, let's have a look at a Python example. I'll just change my font size here. Why did I do that? Okay. So here's this little notebook. If you download the one online, it's complete, but I'll kind of go through this one just to show you how you read the data from these files. As we're loading HDF5, you'll need to import h5 pi. This is easily installed using pip install h5 pi will do it for you, or conda if that's your preference. So we can run that. This next line here just sets the matplotlib as images that we'll make later. And then I've set a base directory to be where I've installed Gremlin. So in this case, it's /user/Niels /BlackboardPowerPoint /Gremlin is where I keep the code. So that's where we'll find the file. Okay, so the first thing we need to do is open the HDF5 file. So we can do that in the following way. Okay, so h5py.file will open the file up to be read. So we use the base directory plus and then the name of our file r10a0.h5. And we're going to open it for read access. Okay. And one of the first things we can do then is list what are the keys in that file. Sorry, list, not lists. And keys, there you go, but the S is in the wrong place. And you can see that there's some different groups of data that are in the file. One called index range. You should mostly ignore that for now. That's actually a relic of the more generic code. Very useful when you have to look at L, M, N, and K indices and knowing what ranges they are computed over. More useful is the params, which is the parameters, and the modes, which gives you the actual mode data. So if you look in the documentation, you'll see the parameters are formatted in a particular way. So we can say params equals f params to extract the data. And then if we just list it all, we can see that these are the parameters that we gave it. So we said, actually, I've got that the wrong way around. So actually, the first parameter looks like it's the radius of 10, then the spin of 0.9. And so these two are swapped around. We then have the energy that's computed for the orbit, the angular momentum, and the frequency of the orbit, the azimuthal frequency. So those are useful things. Okay, so that tells you a description of what the orbit is. We can also check out which modes are available. Again, we can use list keys. So modes is a group of data sets, which will then have data sets beneath it. And we can see, as we saw before, I've computed the 2.2 and the 3.3 mode. And so I can keep running that code, and I can add more components to it if I wish, or add more modes. Although one thing to note, you have to close this file in Python before you can do that. It's a little thing I noticed earlier today. Okay, so those are the data sets that now exist in the file. What we can do is have a look and see, well, what is stored in each data set. So we can do it this way, for instance. That will just store that, but a useful thing to do, check the size of it. We see we have 19 elements, and those are the 19 elements described in that documentation earlier. And so as an example, we take the first element, so 0 in Python, then this is giving you the value of the eigenvalue, the spin weighted Schrodel harmonic eigenvalue. And you can check if you want, and I have time at the end, I'll show you in Mathematica that agrees with what we find in the toolkit. So Scott's eigenvalue, the one he uses in Gremlin, is the lambda, not the A or the E that other people use. So it agrees with other bits of the toolkit, or at least some other bits of the toolkit. The other one that's probably most useful, if you look at that list, and again, if I have time, I'll show this agrees with Mathematica, is if you look at the 13th to the 17th elements, these are the fluxes of energy and angular momentum. So here, the energy flux to infinity, the energy flux through the horizon, and likewise the angular momentum flux to infinity, and the angular momentum flux to the horizon. Okay, so as I said, probably a very useful thing to do is remember to close the file at the end, or else you won't be able to write more data to it. If you want to have more, so f.close will close the HDF5 file. Okay, so one other thing I wanted to show is that using this code, you can compute snapshot gravitational waveforms, and that's using the /GW. So if you just run that with no arguments again, you can see what you have to give it is a base file name. So that's something that's being computed. It's looking for one of these HDF5 files that circeq has computed. It's going to read out that mode data and compute a waveform. You can then set a theta angle, or the cost of the theta angle, some phi angle, and then you can set what is your time stepping dt and the number of steps you want to take, and that will produce a nice little waveform for you. So let's have a go at doing that. So gravitational wave, R10, A 0.5. You have to, this threw me as well earlier today, not put the .h5, and it's asking for the base file name, not the full file name. It will add the .h5 itself. We can do 0.707, so roughly viewing angle pi by 4, a theta of 0, a dt of 0.1, and we can compute it for 1,000 steps, let's say. And that doesn't take very long. That's probably quite a short waveform, actually. So let's do a stepping of m equals 1. And you can see this has created a file called r10 a0.9.wave that contains the waveform. Okay, so we can have a quick look and see what that looks like. So we can load that using NumPy. So that file is just a text file. So we can use load txt, and again, base directory plus in this goes r10 a0.9 wave. Okay, and that's no errors. That should have loaded that. And then we can go ahead and make a plot there. So I'm just going to cut and paste that in the interest of time. So just going to put a grid on it, so the label, and then just plot. The first column is the time in a-dimensionalized units, and again the second column is going to be h plus in a-dimensionalized units, and the third column h cross. And there's a couple of extra things in there involving psi4 described here. So we can plot that, and as you can see, there's the waveform. This is quite far away from the black hole. It's not the most exciting thing. A bunch of sinusoids. It gets more interesting if you go in closer to the ISCO. And actually, I might run that just now. The other thing to note is it's only using the modes that it finds in that file. So that's added together, the 2-2 mode and the 3-3 mode that I'd put into that file. But that's all. So we go back to Gremlin EQ. Let's change the radius to 2.4, so close to the ISCO. Make a file called R2.4A0.9, and we'll compute the 2-2 mode. And while we're here, why not add in the 3-3 and let's say the 4-4. We can then make a gravitational waveform for that. Again, let's do it 0.707, 0. What was the last? Oh, yeah. Steps of 1 and 1,000 steps. Ooh, that was unexpected. So it's complained because I forgot. You mustn't add that .h5. Take that off, and that will then compute a waveform. You can now see we've now got an R2.4 0.9 dot wave. So if we load that one up, our waveform. Hopefully it's a little bit more interesting in its features. There's a lot of features in there. So let's take 100 steps, 0.1. Kind of expand that out a bit. Okay, somewhere in between those two. There you go. I could obviously just truncate the previous data as well as the way forward. I want to get something that's densely sampled. Right, okay, so you can start to see some features of the waveforms. Even that is still not enough. Okay, so that's the waveform. Now, it has actually, I can just tell by looking at it, I have not added enough modes. I only added in the the 2-2, the 3-3, the 4-4. I probably want to add in the 3-2, and so on. And you'll see things get a bit smoother. These little sort of strange features will vanish, and you'll get a kind of more sinusoidal looking thing. Okay, so that's computing the waveform and showing things in Python. How much more time do I have?
A minute or so.
What, 1 minute?
Right.
Okay. Great. Okay. In that case, all I will say is inside the data files that I gave, there's also a wrapper.cc, which is a replacement for a file that you'll find in /source/exec. You can replace this wrapper.cc here. The whole point of Gremlin is you can kind of wrap around the functions that are built into it. And so what that does is it computes just a bunch of fluxes. It computes the 2-2 flux at a bunch of radii between the ISCO R0 equals 6, the Schwarzschild ISCO, and R0 equals 100. And that's the kind of data you would need to drive an in-spiral. And in fact, if you look in the Mathematica notebook I sent, as well that's included, this goes through and actually makes comparisons. First of all, it makes comparisons between Scott's results and the Mathematica notebooks, Mathematica packages. So check that the harmonics are the same, that we get the same property of the GD6, and also check that we compute the same fluxes, and you'll be able to see that indeed that happens. And you can compare that data with the results from the toolkit. So it's convenient as a reference. Again, I plot a waveform very similar. And this time I'd added a few more modes. And then the last thing I did is that wrapper.cc will give you a load of data for the flux. You can compare that, as Chris showed us in the previous talks, to the PostNewtonianSelfForce series, and that's a very high order series, 22 PN. So it actually agrees very, very well across the entire parameter space, all the way down to the ISCO. I think you get about 5 or 6 digits of precision at the ISCO with such a high PN series. So it does that comparison. And then finally at the end, I just interpolate the 2-2 flux and drive a computer quick-in spiral just using the 2-2 flux as an example. But as it sounds like I'm out of time, I'll finish there and take any questions.
Okay, great, thanks. Well, there were some questions about whether it's the code is for eccentric orbits or not, and which version of the code is actually in the toolkit, but that was mostly answered. So the Gremlin Aqua is just for circular orbits in the equatorial plane, right?
That is true, yeah. So it works for arbitrary spin of the massive black hole, but at the moment it's just for circular orbits in the equatorial plane. As I said, Scott obviously has a generic code. The plan is to open that up as soon as possible. It just takes time to make those changes. We should also say that the Teukolsky code in the Mathematica code, we also have code kindly donated to us from Martin Vanderment, which does fully generic orbits as well. And so roughly on the same sort of timescale over the next few months or so, we should at least have eccentric orbits in the equatorial plane, and then probably move up to fully generic orbits in the not too distant future.
So there was also some confusion about the waveform which you showed. So this is also a circular orbit, but you're viewing it at an inclination, right? The waveform which you are showing.
Yeah, that's correct. So I was showing the plus and the cross polarizations, and yeah, they were being viewed at a not from edge on or from face on, but from some angle, and that's why you kind of see those features. And as I said as well, some of those features were just because I hadn't had enough modes, and so you hadn't really got convergence yet of the waveform. But if you just add more modes into the calculation as I was doing, you'll see it converge quite quickly.
Okay, great, thanks. So I suggest to move the rest of the discussion to Slack, #Gremlin, and we should move on to, so thanks again, Niels, for the talk, especially, prepared overnight. And we should move to the showcases. So do we have Philip here? Philip Lynch.
If I can unmute my mic. Yeah, there we go. Let's see, can you hear me? Is my mic working? Is that good?
Yeah, we can hear you.
Okay, great. Let me start sharing my screen if I can find that.
Philip Lynch will talk about the osculating orbital elements package. So we see it very fine, and I think the font size is fine as well.
Okay, perfect. So as mentioned before, I'm Philip Lynch. I'm a PhD student at University College Dublin, working very closely with Niels. And over the last while, I've become very interested in what happens when you have a particle under the influence of some sort of perturbing force, but in a curved background, like say near a rotating black hole. And so its motion follows roughly this sort of equation, which looks a lot like the geodesic equation, except there's now stuff on the right-hand side. And in much the same way that Martin did for the geodesic equation, you solve this by not solving it. You instead use something called the method of oscillating elements, or oscillating geodesics. And what you do is you identify a set of constants, which can be things like energy angular momentum Carter constant plus some initial phases. And you promote these constants to functions of time that are governed by a set of first order coupled ODEs in this form here, which you can easily solve with a numeric solver like NDSolve. So my ideal version of this package takes an input, which is some initial conditions, some expression for the force, and some scaling constant here, which, very reminiscent of the mass ratio, perhaps, if it's the gravitational self-force. It does some stuff, and then it gives an output, which is how these elements evolve over time and the trajectory of the particle. Now, while this is all very reminiscent of gravitational self-force results, and will be very useful for that, in theory, you could put any force you want in here so long as it obeys this orthogonality condition with the particle's forward velocity. So we're going to do a quick example of something like that. Again, for some reason, this needs geodesics thing is not quite working for me yet. So I need to update to a new version, I think. And so I'm going to do an example of a particle under the influence of a gas drag force. And so in Schwarzschild, that means creating a function for the radial and azimuthal components, the contravariant components now, in terms of P and E. And so define those. And we can define some initial conditions along with some sort of scaling. And the idea is we then put this into our Schwarz oscillating orbital elements function with our initial conditions, and we put our force in with this sort of input here, and we save our output to something called Schwarz orbit. And as you can see, what it returns then is TR, theta, and phi, and these will all now be functions of the Darwin parameter chi, which is just how those equations are derived in the literature. And also we output the orbital elements, how those evolve too. And so I can easily access any of these using this sort of syntax here. So say if I want the radial coordinate at chi equals 20, I can find what that is. And so that'll also let you plot various things. So if I want to know the evolution of, say, my semi-lattice rectum, the P, that'll go down over time like this. And I can plot eccentricity, which for this force will actually increase over time. So that's something slightly different. And of course, I can plot the coordinates and get an idea of how that behaves. And so I get a nice little in spiral like this. And in principle, I can do the exact same thing in care, except now I need to give it covariant components, and I need to use all 4 of them, which is quite different from what we had before. And now we evolve everything not with respect to the Darwin parameter chi, but with respect to Mino time lambda. And so these things are quite different, and so they take very different input parameters. We're also directly evolving energy, angular momentum, and Carter constants instead of P and E, but the principle is the same. You define the components of your force, you give it some initial conditions, and you put it all into this function. I've pre-computed this so because it takes 30 seconds that I don't have. I don't want to run over time, but it computes reasonably quickly, and it'll compute it until it either plunges or you reach the limit. And then you can quite easily see how, say, for instance, your energy evolves over time or angular momentum or whatnot, right? And then we can, of course, use these to then plot our trajectory. And again, we end up with a trajectory that looks something like this for a generic Kerr orbit. So while a lot of the things here are already there and work quite well, there's always more stuff that we could add. For instance, right now we have a couple of models that are just built into the package. So we have that gas drag force that I just showed off there, as well as a first order gravitational self-force model that Niels provided me for Schwarzschild spacetime. But ideally, the main thing, so if you have a force model lying around and you want to add it in so people can readily compute in spirals, that'd be great. We'd love to add it. The other thing is we want a user interface or API that contains the Schwarzschild and Kerr cases and all the very special cases like equatorial and spherical orbits and all the rest that can handle that all very seamlessly. And that means making the inputs consistent, especially how we input the forces, which will probably involve changing the underlying equations that are actually being solved. Before I do that, because I've actually rejigged these equations several times in various different notebooks across my hard drive, I'd like some input from the community as to what the best way to do this would be. And that will involve knowing what you guys would like to use this package for. So of course, I'd like to continue the discussion over on Slack. So I set up a channel for this, the oscillating orbital elements, or over on showcases as well. So with that, I think I'm out of time. Yeah, continue the conversation on Slack, and thanks for listening.
Thanks, Philip. That was great, very well timed and very well organized. We should have, so we will move the discussion on Slack, of course. So we should have the next talk by Lukáš Polcar. Is he here?
Yes. Yes, I'm here.
So can you share your screen?
So can you see my screen shared? Yeah.
You do? Yes. So Lukáš will talk about computing the EMRI using canonical perturbation theory. So
thank you for the introduction. And I'm Lukáš Polcar. I'm a PhD student in Charles University in Prague. And this will be a brief talk about a joint project with both of the main organizers of this workshop. And it's about computing the extreme mass ratio in spire using the canonical perturbation theory. So the setup is that we have a Schwarzschild black hole perturbed by a distant ring-like source, and this source is described by this, we can say, Newtonian potential, but the description itself is completely relativistic, and the method which I've used is based on the Einstein's quadrupole formula, which describes for the point particle how it loses energy and momentum, angular momentum during the inspire. So this is described here, and in case of the point particle, this q ij is defined as this, and the key component of this formula is to find out the formula for the trajectory, or for the coordinates as a function of time, and for this purpose we have used the canonical perturbation theory. So this is based on the fact that our Hamiltonian can be approximately for the bound orbits transformed to the action angle coordinates, and in these coordinates the Hamiltonian depends only on the momenta, which are called actions, and the Hamiltonian equations can then be easily solved where these omegas are the frequencies of motion. And in our case we effectively have a 2-degree of freedom system with these r and theta. So these are just spherical type coordinates, and we want to transform them into these angles. And to summarize it briefly, this can be done by a series of canonical transformations, and the new Hamiltonian can be found from the old one by applying several of these operators, which are just exponentials of this V operator, and this is defined as the Poisson bracket. So all we have to find is are these generating functions, and then we obtain the new Hamiltonian, and in a similar manner we can find the approximate formula for the coordinates. We can then find these are the solutions of the equations of motion, and if we want to insert them into the quadrupole formula, we have to also compute the derivatives, and we assume that the energy and momenta change very slowly when compared to this explicit dependence on time. And so once we have all these ingredients, we can compute the fluxes, and to do so we have to average over time, and this effectively means to eliminate these oscillating terms, so we are left with only this one which does not explicitly depend on time. And so the results are these flux equation, and now I can show you part of these computations which are done in Maple. So can you see the Maple worksheet?
We don't see it. You have to share your entire computer screen, or just stop the sharing and reshare.
Yeah, I will stop the sharing and then switch to the Maple, and so you can see first this is the Hamiltonian in the new coordinates. So this is pretty long expression. Nevertheless, the results are quite simple, and they can be shown. For example, here these are the solutions of the equations of motion, and from that we can compute the fluxes. And for simplicity, I've only computed it in the equatorial plane, and in such case the quadrupole formula reduces to these simple formulas, and when we perform the averaging, we obtain these expressions. But this is still very complicated, and to compute such expressions in more general space-times is literally impossible, and so this leads to the numerical evaluation of the fluxes, which is much more easier, and this is performed in these codes, and the resulting figures are here, and this shows the decrease of energy and angular momenta with the coordinate time t. So that's the result for now, and this result applies for the complete space-time, but only in the equatorial plane. So there's still much work to be done, and I would say that's it.
Okay, great. Thank you, Lukáš, for sharing your notebook with us, your code, showing us a little bit. I just want to say at this point that we are not the two main organizers. We are just the local organizing committee, and most of the credit for the scientific program goes to Niels and Barry. So just so that we're clear on that. Okay, so thanks, and we can move the discussion to Slack. We are tight on time because we still have one talk to go from Theo or Theo, Torres, Vicente. Hello, Theo.
Hi. Hi.
We are coming a little bit into the coffee break, but please.
Okay, I'll try to be quick. Can you hear? Okay, I'll share my screen. Can you all see my screen as well?
No.
I think I can't share my screen for some reason.
So Barry.
Yeah. Okay. I think it's working. Can you see it now?
Yes. Great. Okay.
Cool. Thanks a lot. Yeah. So I'm Theo. I'm a postdoc at University of Sheffield, working with Sam Dolan. And I just want to present some work we've been doing on using the toolkit to compute some electromagnetic self-force on the Kerr spacetime. So the idea of our project is to apply the toolkit to self-force calculation, and that's by basically solving the source Teukolsky equations. So we've seen a lot about it so far, so I'm just going to mention the main thing. But thanks to the toolkit, we've seen that we can actually compute some fluxes in the scalar case or gravitational case. So in the Teukolsky package, we've seen that we have this function, Teukolsky point particle mode. And by putting spin 0 or spin -2, we can get some Teukolsky mode objects. And from those ones, we can extract fluxes, radiativity or through the horizon. But what we've noticed is that when we try to apply this function with s equal -1, it says that we have no point particle source available for those parameters. So the goal of what we're doing with Sam is to essentially try to also have a Teukolsky mode object for this s-1. And essentially what this is simply complementing the work that has been done. So what we need to do is compute the radiativity to infinity and through the horizon. So as I've said, using the Teukolsky point particle mode with spin 0 -2, we can also extract the fluxes. And now what we want to do is just compute those fluxes for the electromagnetic case so that we can add it potentially to the toolkit. So to do that, what we do essentially is simply solve the source Teukolsky equations. And this is done by using the Teukolsky package as well as the spin-weighted spheroidal harmonics, because the source in the electromagnetic case is directly depends on these functions. And this works really incredibly well. So here are some plots that we've made. So this is the energy flux, the total energy flux normalized by the Wakefield limit for different spins. So A0 for the Schwarzschild case, and then from different Kerr parameters, black hole spins. So yeah, this works really well. And we've seen also that we can compute those fluxes using the toolkit. And what's great about that is that we can directly compare the result for the electromagnetic case to the gravitational case. So for example, this is just one plot we were able to make to compare the 3 different integer spins, the fluxes of the 3 different integer spins. So that's one way we've been using the toolkit. And another way is to compute the conservative part of the cell force. And for this, we also use the tricky and spin-weighted spheroidal harmonics to compute this, this component. But in this case, it turns out that the conservative part of the cell force is divergent. So we need to regularize that force. And to do that, we use 2 other components in the package. So especially in the spin-weighted spheroidal harmonics, there is this method called spherical inspection, which was very useful because it allowed us to decompose the spin-weighted spheroidal harmonics into spin-weighted spherical harmonics. And then we further need to decompose the spin-weighted spherical to scalar spherical harmonics. And finally, we've used the regularization parameters that were available in the toolkit as well to compute the regular cell force, the regular conservative part of the cell force. So we've done that for the Schwarzschild spacetime. So this is just one plot, for example, where you see the radial component of the cell force as a function of L, and the different colors are the different values of the cell force after subtracting different orders of regularization. So that's what we have so far. So it seems to be working really well. So you see that the blue dots are divergent at the beginning, and then the more you regularize, the quicker the decay is. And the last thing we need to do is now to do exactly the same thing for Kerr. And I guess it will just be using the same functions, and that's work in progress. But yeah, I think so far we've been using the toolkit to compute the electromagnetic cell force. And I think the dissipative part is quite robust now and could maybe be added to the toolkit at some point. And we just need to finish this part on the conservative part for the Kerr case. So yeah, thanks for all the talks, and thank you for your attention.
Okay, great. Thank you, Theo. That was a very informative presentation. So that's all for the showcases. Once again, discussion continues at Slack. Now the coffee break starts. I will just share. Okay, let me see. I don't have the right slide to share. Okay, so the coffee break starts now, and let's meet in 22 minutes again for the rest of the talks.
Okay, so welcome back to the final session of the day. And the first talk of this session will be by Peter Diener, who's going to tell us about his time domain discontinuous Galerkin code.
Thank you, Barry. Can you all hear me?
Yes.
Excellent. Yeah, so I'm a little bit sad that I couldn't actually be in Prague because I've been there before and it's really a beautiful city, but I guess that's it. It is what it is. Anyway, today I'm going to talk about a new code that has just been added to the black hole perturbation toolkit. It was added to the Einstein toolkit last year and doing time domain cell force with discontinuous Galerkin methods. And the code is called SelfForce 1D. So this is in collaboration with Barry and Niels, whom you all know by now. So let me just get on with it. So SelfForce 1D, as I said, is an open source code for performing time domain cell force computations. So what it does, it involves the scalar wave equation currently, but metric perturbation equations are being added as well in a Schwarzschild spacetime. But again, work is underway to add Kerr as well for this. Fields are decomposed into spherical harmonics, resulting in 1+1 dimensional PDEs to be solved using the method line. So where you discretize in the radial direction and then use an OD integrator in the time direction. We use nodal discontinuous Galerkin methods to discretize the PDEs in the radial direction. And if you do things carefully and correctly, you will get exponential convergence with the order of the method being used. We treat the point particle through the effective source for generic orbits in a world tube approach. I haven't heard too much talk about the effective source. I should probably have made a slide for this, but I didn't. So let me just say that the effective source is a way of solving a wave equation, but instead of actually using a delta function source, you analytically subtract off an approximation to the singular field in order to get an equation that in a given region only will actually evolve the regular field instead of the full retarded field. Because we are using just an approximation to the Detweiler-Whiting singular fields, we cannot use that everywhere away from the particle. It's essentially a Taylor expansion in distance away from the particle. So what we have is a world tube approach where we, inside a world tube, use the effective source. Outside we have zero source, and we in that region we evolve the full retarded field. As I said, if you do things correctly, you can get exponential convergence with discontinuous Galerkin methods, with the caveat that the underlying fields have to be smooth in certain places on the domain. The only places where they're allowed to be non-smooth is at the boundaries between the discontinuous Galerkin elements. And so for that reason, we need to, and also because the effective source has limited smoothness at the location of the particle, we need to keep the particle at boundaries between elements. And the easiest way to do that is to use time-dependent coordinates where the coordinates are shifting around, except for the particle always being on the same computational coordinate. So in addition, we also want to be able to go all the way to the horizon and to Scribe plus. And so we use hyperboloidal coordinates that was discussed earlier today as well, near the horizon at Scribe plus, and either time-dependent or tortoise coordinates in between. Tortoise coordinates only if you're looking at circular orbits. So our computational domain covers everything between the horizon and Scribe plus. And as was mentioned earlier, when you use hyperboloidal slicings, you don't actually have to provide any outer boundaries because there's no fields, no modes coming in at the boundaries. In the code, we also, of course, have to evolve the orbit of the particle, and that is either you evolve using direct geodesic integration with forces, or through the oscillating orbits framework that was mentioned just a few moments ago, and again also with forces. We have implemented both Munkakota and Adams-Basford Moulton multi-value method to do the time integration. We have code in there that can extract the self force from the regular field at the particle location. We have implemented other observers that can extract the fields at the horizon at Scribe plus. And we can use initial data calculated in the frequency domain by a code, a Python code by Niels, so that when we do eccentric orbits, we do this for the low L modes in order to having to avoid to evolve for a long time before sort of initial transients leaves the computation domain. We have the ability of turning on back reaction, but there are still some issues with instabilities once we actually go to try to get full accuracy in the extracted self force. The code is written mostly in object-oriented Fortran, but the effective source is written in C++, and that was written by Barry. And the initial data code for generating initial data was written in Python by Niels. So the code requirements are the following. It needs a fairly modern Fortran compiler because of the object-oriented features that has been added in later versions of Fortran. On my laptop, I have successfully compiled it with both GFortran 7.3.0 and iFort 17.0.7, but also on other machines with newer compilers. It also needs a C++ compiler because of the effective source. Either G++ or ICPC should work. Then it needs Python. Also, not only because we have the initial data solver in Python, but also because it uses a tool called scons for building instead of make. This is a very easy to install Python code that can be installed using PEP. For numerical libraries, we just need BLAS and LAPACK. Very small subset of those routines are needed for some small matrix eigenvalues and matrix inversions. And then we need the GNU Scientific Library for spherical harmonics and fitting. And I should also mention that all the classes implemented in the code are available at this URL here. This was essentially similar to Doxygen. Fort is a tool that is specifically written for modern Fortran to extract all the documentation that you put into your code itself. So that's the design of the code, as I said, relies on object-oriented programming ideas, both to expose and exploit modularity whenever possible. And so it's implemented in modern Fortran 2003, 2008. One of the basic concepts is an abstract equation class that knows nothing about the actual equations, but sort of defines the interface to certain type-bound procedures, which is what Fortran calls C++ member functions, that any derived equation class has to provide. On top of that, you then have some additional classes that know about the data structures needed. For example, ODE integrators or ODE equations or PDE equations, they need different kinds of underlying data. And then on top of those, you can then implement the actual equation systems like the geodesic evolution, oscillating orbits evolution, and scalar wave equation. And then when you do that, the time integrator need only know about the type-bound procedures as defined in the abstract equation class, and then will call the actual implementation of these by the various equation classes. And thus, hence, is completely agnostic about the underlying data structures. So the communication between equations are then done through external data types where, again, different equation class can write and read data without knowing about each other. Many of these things are sort of inspired by Cactus and in the Einstein toolkit. Just as a basic example, here's the abstract definition of the abstract equation class. So up here we have the abstract, so that means that that all these routines type-bound procedures are not actually defined here, but will be defined by classes that inherits from this. And so you can see we need to have an initialization routine. We need to have a routine to calculate the right-hand sides. We need a routine to set certain fields to 0. We need routines to update the variables in a certain way. I will get back to that in a moment. And then we have routines to save information that is needed by other equations. And of course, we have some, and also to read information specified by other classes. And then, of course, output routines. Just to delve a little bit deeper. I'm sorry if this is a little bit boring from some people, but I thought it might be instructive. The routine, the interface to the update vars routine looks like this. So essentially, it's something that is called on a class, so it needs to know what class is called on. And then it has two source information about possible two sources, a destination, and some scalars. And the convention is that if the source is passed in as -1, it means the right-hand side variable. If it's passed in as 0, it's the actual state vector. Or if it's passed in as a number between 1 and n temp, is one of the temporary variables that are maybe needed by an evolution system. So essentially, you can do an update like the following, where you say, okay, the state vector should be updated to be a scalar times the right-hand side plus another scalar times one of the temporary variables. And this is typically what you need in a method of lines evolution. So, and these routines is actually something that is provided by a PDE equation class. So it's below the actual implementation. So once that has been written for a certain type of equations, the user can write equations classes to actually implement systems without having to worry about these details. But going back to the computational setup, so here is a little figure that shows what is happening on the computation domain. So here on this side, we have the horizon. On this side, we have Skoupý+. And in a region between the horizon and the coordinate location T1, we're using hyperloidal coordinates tau and rho with ingoing hyperloidal coordinates. And we evolve the full retarded field. Between T1 and W1, we use the time-dependent coordinates lambda psi. And again, in this region, we're evolving the full retarded field. Then between W1 and W2, this is the so-called world tube. We are evolving only the regular field, and again in the time-dependent coordinates. And then again, the things repeat on the outside between W2 and T2. We're evolving the full retarded field using hyperboloidal coordinates, time-dependent coordinates. And then between T2 and Skoupý+, we are evolving the full retarded field again, but in this region with outgoing hyperloidal coordinates. So in the numerical scheme, of course, internally, we have to make sure that we handle these boundaries correctly when we calculate the fluxes that are required in the discontinuous Galerkin methods. But this is, again, just doing coordinate transformations between various coordinates at these locations. And here also add and subtract the pieces of the singular field that is needed to convert between the retarded and regular field. So the code uses a Fortran feature called namelist for reading input parameters. So it essentially a simple parameter file looks like this. You have ampersand params at the top and then a / at the end. And then you have all the named parameters that are defined in the params name list equal to some values. They can be strings, they can be integers, they can be real values and so on, and logical values. But let's go and do some examples before getting to the end here. So let me just minimize my Can I minimize my, yes. And let me get this one started. So I provided some examples, a table with some examples, and if you extract the examples, is to create an examples directory that has a README and 2 different directories for the 2 different cases that I'm going to look at here. Down here, I changed into the Scholar Gaussian order 10 directory. And I'm just going to start my executable here. So I use the time command just to get a feel for how long time it takes. Use the relative path towards to the executable that has been built inside my SelfForce 1D build directory. And then I provide the parameter file as input. So print some stuff to the screen, but let's take a quick look at the parameter file. So here I'm saying that I should use the scalar Schwarzschild evolution equations. Here I'm saying that I want to have 32 elements, discontinuous Galerkin elements, each of order 10. So each element will have 11 nodes. I specified the coordinate, the minimum or the minimum coordinate on the grid -20. Then I specified that I want a Gaussian pulse or Gaussian initial data centered at coordinate 10. The mass of the black hole is 1. I want to evolve L min to L max from 0 to 2, from 0 to 1000 in units of m. Sigma and amplitude of the Gaussian is 1. And then I activate my field observers to extract data at the horizon and Skoupý+. Here, that since it's just a particle, there's no time-dependent coordinates, but I still use hyperboloidal up to a certain region. The size of the region where I then use tortoise coordinates is determined by default values of some other parameters that are not listed here. Let's see, it's still running. Oh, it just finished, 95 seconds. So before going in and looking at some of the data, let me go to the other directory and get that started, because that takes a bit longer, and we can talk about that afterwards. Okay, so that is running. So doing after the run, there's been some files created. These files with pi with a variable name. Pi is the radial derivative, psi is the field, and rho is the time derivative of the field. These are different modes: L equals 0, m equals 0, L equals L is 1 equals 1, and then 3 and 4 is L equals 2, m equals 0, and L equals 2, m equals 2. And extract just means that it's the field is extracted. I have provided some GNU-plot scripts to look at the data. So let me just get that started. So I start up the GNU-plot command line, and then I can load my scripts. And the first one will be this one. And let me make this a little bit bigger. So what you see here is in purple is the data extracted at the horizon. Actually, no, wait a minute. I wanted to start with L equals 0. So purple is data extracted at the horizon. Green is extracted as Skoupý+. Here I'm plotting in a log plot So as you can see, the tail behavior is actually visible at the end, and I get the correct tail behavior. So I get t to the minus third power for the data at the horizon, and I get t to the minus 2 for the data at square plus. As you can see, we don't have many cycles before we get into the tails here. I guess it's, but the good thing is that even with a short evolution time like of 1.5 minutes, that that actually you can actually see that we are getting that the code is getting the correct tail behavior. Looking at L equals 1, you can see we have a little bit more of the cross-normal mode ringing before we actually get to the tail. And again, for L equals 1, we would expect t to the minus 5 at the horizon and anywhere in between, but only t to the minus third at square plus. And let me just also show you L equals 2, where you can see that at square plus, we do see the tail behavior with the correct t to the minus 4 decay. But here you can see we have so many, the quasi-normal mode phase is so long that we essentially drop down about 15 orders of magnitude in amplitude of the field. And eventually we are limited by the truncation error of the method. We could probably push that by going to higher order, but then eventually we'll be limited by round-off error instead. And so at least with this setup, it's, unless you go to quad position, I don't think you would actually see the L equals 2 correct tail behavior. Also wanted to show you the quasi-normal modes. I'm not going to show you that for L equals 0 because we have so many, we didn't have very many cycles, so it doesn't make sense. So what I'm plotting here is just in a log plot, the amplitude again at the horizon at square plus as a function of time. And what I've done is I've extracted, or I went to Emanuele Roberti's homepage and extracted the correct or the analytic, semi-analytic frequencies for L equals 1 in Schwarzschild for a scalar field. And the blue curve that you see agreeing quite well for a long time with the horizon data shows that I am getting both the right decay rate and right real frequencies here. At the end, of course, when you start to see the transition to the tail, and so of course you will expect to see some deviations once you get to that point. Also, you can I haven't plotted that on top of this the data square plus, but you can see that also at least in the eyeball see that the decay rate and real frequency is the same at the horizon square plus. And correspondingly for L equals 2, we have a lot more cycles, and you can see that we have really good agreement all the way down to where we start to see the errors from the or the truncation errors of the method. And up here we do have the correct or the transition to the tail behavior. So that was just an example with just evolving the scalar wave equation with no source, just to show that both the tail behavior and the cross-normal modes come out correctly. So let me exit that and then switch over to the other job, other test that I started. And let me show you the parameter file here is a little bit more complicated. We again have the equation name. Here I actually use 128 elements because I have those 3 different regions with two regions that have local coordinates and one with time-dependent coordinates. I'm only using 6th order methods here. I set the minimum radial coordinate to -30. Here I specify that I want an eccentric orbit with P of 9.9, eccentricity 0.5. This T size determines how big the time-dependent coordinate transformation region is in terms of the whole domain. And I turn on the effective source by saying use particle equals to 1. Again, we have mass equals to 1. I'm doing Lmin equals 0 to and Lmax equals to 2. The Gaussian center has no importance here. T initial to T final from 0 to 600. That is just a little bit more than one complete radial cycle here. I turn on the world tube. I use generic orbits and I use the oscillating orbit interface. Set the world tube width in terms of complete elements to 4. And I use exact initial data from Niels's Python code for all modes up to from 0 to 2. And they are in the current directory, and their base name is given by that. Because Niels's Python code has a different convention about the initial phi value than what I would normally have in my code, I have to specify an initial phi value in order to get everything to match up. Since I'm using initial data, I can turn on the effective source at full strength initially. Otherwise, I would have to turn it on smoothly in order to avoid some non-physical solutions. T sigma T order determines essentially how smoothly this turn on would be if I actually used it. I set the charge to 1/8, set the mass to 1, and then I don't turn on the back reaction in this run here. So if all orbit is false and I don't have enough L modes to fit the high order terms in the sum, so I have that turned off as well. So here I don't extract data at the horizon of Square Plus. What I do is I extract the self force at the location of the particle. These are the Schwarzschild wave.f files. The FL file has the field at the location of the particle. FIL has the phi derivative. FRL has the radial derivative, and and FTL is the time derivative. So I prepared a little GNU plot script that will plot the radial component as a function of time. So let me just, I should do it inside GNU plot, of course. And you can see we already have quite a big portion of the orbit. Hang on, why did that pop up there? Let me just make this window bigger. Replot it. And so you can see that I have the radial component of the self force for L equals to 0 for the purple curve, L equals 1 for the green curve, and L equals 2 for the blue curve here. And you can see that the L equals 0 mode goes, or L equals 1 mode has some zero crossings, which is why you have these features here. And you can see that because I use the right initial data, I get the right self-force from the beginning. If I didn't do that, then there would be a lot of transients that I have to wait for it to settle down. And for L equals 0, that takes quite a long time because there's some unphysical modes that decay slower than what you would really expect that get excited if I turn that on in a smooth way. With GNU-POD, you can press E and then see an update of the plot as it continues. I'm also plotting, outputting information about the orbit. And so if I plot that, you can see that we started down here and have gone through the closest passage to the black hole, and now on the way out again, maybe we had already passed the furthest point again already. Maybe while I have this stuff open, I should ask if there's any questions so far. I can't see the chat right now, so if somebody can let me know.
So there aren't any questions in the chat right now, but if anyone wants to ask one, I'll let you know.
Okay. So let me, so this will just continue a little bit until t equal to 600. Otherwise it will continue to look mostly the same here. So maybe I should just go back to my final slide and talk about the future improvements and developments. So there are other systems or creations in the pipeline. Last year, my IU student, Sarah Skinner, implemented Teukolsky in Schwarzschild and start working on figuring out how to do the mode coupling in Curve for 1+1 code. And just today, I have another IU student, Shio Gibbs, starting, who will continue that and hopefully be able to get that to work, and it can be added to the code by the end of the summer here. Metric perturbations in Lorentz gates are under development by Samuel Kapp, my graduate student. And we also have a code in development for the ReggeWheeler Severely metric perturbations. That is mostly me for the moment. Another feature that would be good to have, but we don't have yet, is checkpointing restart. But I have another IO student just starting again today, Mary Ogborn, who is going to attempt to get that working this summer. What I really need to get done is a code documentation document explaining how all the classes fit together sort of in the overall structure. I have, as I mentioned, a code documentation of all the different classes, but I need to write something to describe how everything fits together and what the overall design ideas behind the code is. I think I mentioned that the code is part of both the Einstein School toolkit, and then just earlier this weekend got added officially to the black hole perturbation toolkit as well. So hopefully the code will be a useful community resource that will inspire new developments that hopefully people will contribute back to the toolkit so it can benefit everybody else. And that's what I had. So let's go to questions if there are any.
Okay, thank you very much for a very nice talk, Peter. Are there any questions from any of the participants? So we can also follow up with questions in the Slack channel afterwards. I think there should be there's a Self-Force 1D channel.
Yeah, so probably as soon as the meeting is over, I will have to go and get some food, and then I have some other meetings today, but I will definitely be online tomorrow doing the development stuff going on there. So I'll answer questions tomorrow probably.
So there's one question here in the chat from Leo Stein.
Okay.
He's asking, is the Kerr code going to be fully spectral in the angular domain? Maybe you could give us more details on that.
Yes, I mean, it will be decomposed into spin-weighted spherical harmonics, but then still, when you do it in the time domain, you still have coupling between modes, and so you have to. The modes are not evolving independent in a time domain code. So, and that was what Sarah Skinner worked out last summer, how to get that done, and this will be implemented by Show this summer, hopefully.
Okay, thanks, Peter. Hopefully that answered Leo's question.
Otherwise, we can talk about it later.
Yep. Are there any other questions? We have about 5 minutes until we start the next talk. So if there are questions, feel free to post them in the chat. Okay, so I suggest any follow-up questions we can ask in Slack later.
Okay.
And Peter, you can check back in the Slack later.
Yeah.
I think particularly people might want to know how to get up and running, compiling the code and installing.
So if there's any problems with that, please let me know. I mean, I've done it on a few machines myself, but of course I haven't covered all the compilers and stuff like that. And there might be some. Actually, maybe I should, before stopping, just go to the actual. Oh, I stopped sharing. Hang on, let me get back. Just if anybody have problems with the installation, it's fairly simple, I think. It doesn't really need that much. Let me just go to the Self-Force 1D directory here. And since it uses the sconst tool, there's an sconstruct file. I have one here for the GNU compiler on my laptop, the Intel compiler on my laptop, and a different machine. I have a generic for Fedora. But the sconstruct file has a bunch of stuff in the beginning defining what compilers to use and so on. But what you really should be interested in is if you have your libraries installed in different in non-standard places, you probably want to modify the environment variables here for the libs and lib path. And again, this is a Python tool, so essentially this is just Python list of strings. So comma separated strings inside square brackets here to list all the libraries that is needed, and you can also list multiple library directories to where the code can find it. So okay, so I think that's should be enough to point people in the right direction.
Okay, that's great. Thank you again very much, Peter.
I'll stop sharing then.
Yep, and we'll have Michael start preparing his talk, and we'll actually maybe give 3 minutes just in case anyone was planning to join, and we'll start at 1:15.
So maybe if Michael has any kind of slides or notebook that he would like to share, I can put it online on the website. Or
yeah, so I have a set of slides I can send you separately, but they should be showing right now, I believe.
Yeah, it's showing. Great.
Yeah, so I'll wait a few minutes till 10:15 and I'll start.
Okay, so it's 1:15 now, so we'll go on to the next and final speaker of the day, who is Michael Katz, and he's going to tell us about the EMRI Kluge sheet that he has been developing with Alvin Chua.
All right, well, I'm assuming based on before you can all hear me and see my slides, so let me know if that's not the case. So first of all, my name, once again, is Michael Katz. I'm a finishing PhD student at Northwestern University. I'll be starting a postdoc in the fall at the AEI in Potsdam. So I look forward to working with you all more when I head over there in the fall. Today, I'll be presenting data analysis calculations with the EMRI Kluge suite on behalf of myself and Alvin Chua, a close collaborator of mine, and someone I'm sure you all are somewhat familiar with. And specifically, what we'll be focusing on today is calculating signal-to-noise ratios in LISA. I'll get into why and everything as we go, but kind of the progression of what we'll see here, both in this short talk and the tutorial that we'll do in a Jupyter notebook, is we will first look at the Kluge suite. We'll generate some waveforms. We'll use those waveforms with the LISA sensitivity curve to generate signal-to-noise ratios. And then we will explore the parameter space of EMRIs to understand how changing different parameters affects our signal-to-noise ratio and therefore our ability to detect and characterize sources. So before I begin, I just want to say kind of two things up front. One, I put install instructions into the Slack for the EMRI Kluge suite. If you have not installed that and you would like to kind of follow along with the tutorial, please go to the Slack and look at the install instructions and try to take care of that before we start, which will be in about 15 minutes. I'll leave a few minutes to correct any install errors if we can, but otherwise we'll just kind of move on. So if you want to do that, please go ahead and do that. The other thing I'll say is, while today we are talking about the EMRI Kluge suite, the signal-to-noise ratio calculations that we do are not specific to the Kluge suite at all. So if you have a waveform in the future that you want to look at, the detectability of it with LISA, you can use the exact formalism that we will show you later to do that. So there's nothing specific to the Kluge suite. So, down the line, if you have a waveform you want to test, you can go ahead and use the machinery that we've given you here. Okay. So first we'll start with the Kluge suite. So the Kluge suite is a collection of 3 Kluge models shown there on the bottom: the analytic Kluge, the numerical Kluge, and the augmented analytic Kluge. So what is a Kluge model? Well, it's a semi-relativistic approximation to an EMRI waveform or EMRI orbits in order to create a waveform in a shorter amount of time. So something that is faster than the general waveforms that you all are working on that are, in much more detail than these types of waveforms. Effectively, what this means is that we'll be using an end-to-end waveform generator where you'll put in parameters and we will get out a waveform or the Lisa response version of the waveform, if you prefer. So it is something that can effectively be directly used in data analysis algorithms. So why do we want to use these approximations? Well, I'm sure as you know, as you go to higher fidelity models, the waveforms and the trajectories take longer amounts of time and are therefore not as easy to use directly in data analysis. So on the data analysis end, we cannot wait until the higher fidelity waveforms are ready. We need to be preparing our algorithms, testing our algorithms, doing things like that right now. So right now to do that, we're using these Cluj models. It's not ideal, but it's something that we have to do. Something that we have to do right now in order to prepare for the mission properly. I just saw Niels' comment there. So yeah, so the notebook today is in the examples folder of the EMRI Cluj Suite repository. So once you clone it, you will have the notebook as well. So I'll just go through briefly some of the kind of high level points of differences in the Cluj models. I'm not going to go through all of this, but take a look as you please in terms of the details of how each part of the waveform is generated. But so at the top, you have the analytic Cluj. This is generated with mixed order PN fluxes to create the trajectory, as well as a Peters and Matthews approximation to create the waveform. Ultimately, the analytic Cluj is fast, but it's not very accurate. One reason it's not very accurate is its instantaneous frequencies are much higher than the frequencies that we see in Kerr or in the numerical Cluj or things like that. So ultimately, the advantages of the AK is that it's fast, but the disadvantages is not very accurate. And we generally recommend it only for qualitative use only and not for any high fidelity applications. I will caveat that by saying the AK is currently the waveform used in the Lisa data challenges for the EMRIs. However, I believe the next round of Lisa data challenges, we will be switching to the AAK. On the bottom, you have the numerical Cluj. This is the slowest, but also the most accurate of the Cluj models we have. It fits its trajectories to adiabatic trajectories, uses the quadrupole approximation to generate the waveform. And ultimately, this creates waveforms that are accurate in comparison to adiabatic waveforms down to pretty close to the ISCO radius. I see a question there, quantifying fast. I'll get to that in one second here. So ultimately with the numerical Cluj, what we get out of it is a slower waveform, about an order of magnitude slower than the AK or the AAK. But ultimately it's the most accurate of the Cluj models. Now, once again, the Cluj models are overall not very accurate. So the fact that it's the most accurate of the Cluj models, isn't saying too much, but that's in comparison to the other two, that's how it is. So in the middle, you have the augmented analytic Cluj, which is the best of both worlds. It's effectively the beginning of it is the numerical Cluj, and the end of it is the analytic Cluj. So it fits its trajectories to the numerical Cluj, and it maps the frequencies of the numerical Cluj onto the frequency basis of the analytic Cluj, and then generates the rest of the waveform in the analytic Cluj framework. So this results in getting waveforms that are accurate with respect to the numerical Cluj for about 2 to 6 months. And beyond that, it starts to deviate. Ultimately, the timing of the AAK is fast, so we get that advantage that the analytic Cluj gives us, but it's not as accurate as the NK, as we just discussed. So when we talk about fast, what we really mean is somewhere more in the realm of something that's usable in data analysis. So if we work on snippets of, say, 2 months or a few months or so, generating waveforms with the Cluj models is generally okay in terms of its speed for doing data analysis. But once you go more towards a year waveform, which is what we hope to be working with when we actually do the data analysis, it becomes much too slow. We're talking about order 10 seconds up to 100 seconds for a singular waveform to be created. And if you work through the workbook that we'll do here in a short amount of time, you will see this. You'll see how long these waveforms take when we generate year-long waveforms. And that makes them effectively not usable in data analysis in terms of generating full year-long waveforms, because we cannot afford to generate waveforms in tens of seconds to do data analysis. Generally speaking, in data analysis, we need to generate waveforms on the order of milliseconds or tens of milliseconds. If we start getting above there, we start to have, much more problems in terms of convergence in our algorithms. I will quickly mention here that I have contributed a GPU implementation of the AAK to the Cluj suite. I'm not going to talk much about it today. All I'll say about it is that it's about 1,000 times faster than the AAK. It does a full waveform for a year-long waveform in about 30 milliseconds. And we are using it now in parameter estimation like studies. And the algorithm itself for the GPU implementation is generally more designed towards data analysis applications rather than just waveform generation. So if you want to use the GPU AAK, feel free to contact me offline and we can talk about it. But other than that, I'll kind of leave that for offline discussion if you're interested. So once we have the Cluj models in hand, we want to look further down through the downstream at LISA data analysis. Now, I personally think this is very important to share to the group of you all who are working on waveforms. Obviously, working on waveforms is extremely important. Without accurate waveforms, we can't do anything in terms of our analysis. That's obviously an extremely important step in the analysis, but obviously that's not where the analysis ends. So I wanted to give you all kind of a high-level picture of things that we care about in the LISA data analysis realm, because that affects how we will analyze EMRIs downstream once we have the waveforms that you all produce in hand. So ultimately, what is our goal with LISA data analysis? It's to find sources, extract accurate parameters, and do things like test GR amongst other types of things. And these sound obviously great, but they're relatively hard to do in the LISA analysis framework. And I will kind of try to draw comparisons with ground-based observing in case you're more in tune with what ground-based observing has been doing, just so we can kind of compare and contrast the two. So the first major thing that LISA has to contend with that ground-based observing doesn't is overlapping signals. So on the right, you'll see a plot from the LISA mission proposal. It has the sources that we care about in LISA, or the main sources, I should say. So it has the massive black hole binaries, the galactic binaries, EMRIs, and stellar origin black hole binaries. All of these sources will be evolving in the LISA data stream all at the same time. So all of these gravitational waves will be overlapping with one another as they enter the detector. And our job as data analysts will be to disentangle all of these signals while still maintaining the scientific goals that we want to with each signal or with populations of signals and things like that. So it's definitely something that is difficult and definitely not a solved problem yet in the data analysis community. In ground-based observing, they expect generally one source in the data stream at a singular time, making it, I'm not going to say easier to analyze, but it's different analysis. You don't have to worry about disentangling multiple sources. In a similar way, our data stream in LISA will never be void of sources. So from the moment we turn on the detector to the moment we turn it off, it will have gravitational waves in it. We know that's true from galactic binaries, but most likely from other sources as well that will exist for years over the course of the observing period. And this makes it much harder to estimate the noise, which is an important part of our analysis, as you'll see in a few minutes when we start looking at signal to noise ratios. In ground-based observing, you have long stretches of time where they don't observe a signal, and they can use those long stretches to estimate the properties of the noise. This is no longer true in LISA. We will have to estimate the noise while we estimate our signals. So it's a little bit less straightforward in terms of being able to characterize the detector versus the signals you measure and all of those kinds of things. Additionally, we'll deal with some other effects. A very important effect that we have to consider is non-stationary noise. This can be somewhat important to waveform people just in terms of understanding what it is. So over time, we expect the noise properties to change. This is not true in ground-based observing. In ground-based observing, the time it takes to observe a signal is short. We do not expect noise properties to change over that duration. In LISA, that is no longer true. Over the years that we'll be observing, we do expect the detector properties themselves to change. Additionally, we'll be looking at non-Gaussian noise, which is generally the name given for glitches, if you're familiar with that from ground-based observing. And one thing that we'll also have to deal with is data gaps. So when we look at long waveforms, we will have to contend with gaps in the data every week or so. It's not been fully determined what the gaps will be, how often they'll be, when they'll be, things like that yet. But what that means is we'll have to take the detector offline, or the spacecraft offline, to do maintenance, to reposition its orbits, do things like that. And we won't be able to make measurements at that time. So we'll have actual gaps in our data, but we'll have to contend with in terms of what we do in our data analysis algorithms. So I'll quickly touch on parameter estimation for EMRIs. I'm not going to get into too much detail, but for EMRIs, we're looking at long signals on the order of a year or so. In order to detect these EMRIs, we need many, many cycles for detection. Generally, I think the kind of minimal amount of time that people expect it to take to detect an EMRI is about 2 months or so of observing. So obviously you can kind of extrapolate to the number of cycles that is. EMRIs are difficult for search in PE because of their very complex harmonic structure and potential harmonic overlaps between different source parameters in the parameter space, which can make it very hard for us to converge our algorithms and to create and tune algorithms efficiently to do this. Now, currently, like I said, we're using the Cluj models, but I want to briefly mention that we ultimately have to go beyond the Cluj models to more accurate waveforms. And I'll quickly mention that myself and Alvin and Niels and Scott Hughes are working on a fast and accurate waveform generator for EMRIs that leverages specialized hardware, which is GPUs, to do fast calculations, as well as very, very good data science-like techniques to accelerate different parts of the waveform generation process. So that's something we're working on that you'll probably hear more about in the next month. But if you have any, questions on that, feel free to reach out and ask. So ultimately today in the tutorial, this is what we will be doing. We'll be calculating the signal to noise ratio. So once again, this is effectively a way for us to estimate whether or not a source will be detectable, as well as how well we will be able to characterize that source. A high SNR source will be easier to characterize. A lower SNR source will obviously be more difficult to characterize. So to do that, we do the complex noise-weighted inner product shown here on the left. And when we're talking today, we'll be talking about what's called the optimal signal to noise ratio, which is kind of given down here, which basically means we're taking an inner product of a signal with itself. So A with A. When we actually do analysis with data, and we instead of doing A with A, we do A with a data stream, we expect the signal to noise ratio to be distributed about this optimal signal to noise ratio with this value as the mean. So to do this, we'll have two time domain signals. In this case, it will be one, just A of t. We'll take the Fourier transform here, and I'll just quickly mention, as we'll see in the notebook, that you have to be a little careful about how we do this because we'll be using discrete Fourier transforms rather than full Fourier transforms. So we have to be careful considering this formula and this methodology is written as in the kind of full Fourier domain with full Fourier transform. And this last term here that I quickly want to mention is the power spectral density of the noise. So this is what I was talking about with estimating noise. This is where it comes into our analysis. We need to understand the noise at across our frequency band in order to fully understand how that affects our observing. What we want from this is we want to downweight frequencies that have high levels of noise, and we want to kind of upweight frequencies that have low levels of noise so we can focus more of our analysis on the areas where we can make better measurements effectively. So that's what this effectively accomplishes. We'll also be looking at plots like this today, which is a plot of the characteristic strain. I'm not going to get into too much detail about what the characteristic strain is. We'll talk about it a little bit more in the notebook. But what effectively is the amplitude of a source normalized by the frequency bin that it lies in. But the important part of it is that it lets you do something that we say integrating by eye, so determining the SNR by eye very roughly. And really, it's not even estimating it, it's not approximating it or anything. It's just a way of kind of qualitatively assessing what you think the SNR will be and comparing different sources. So here, for example, waveform 1 has a signal to noise ratio of 22. For waveform 2, there's a signal to noise ratio of 2. So the red one is not detectable, the blue one is detectable, and you can kind of visually see what that difference or kind of how those differences play into the signal to noise ratio just by kind of integrating this area here by eye. You can kind of see that. So ultimately, we'll switch over the notebook now. I wanted to make sure that most of this was kind of more hands-on tutorial. So what we'll do in the notebook is we'll look at the least sensitivity curve. This will be very brief. We provided a function for you to just input a frequency array, and it will give you the sensitivity curve, so nothing in too much detail. We'll then generate AAK waveforms. We'll use numbers 1 and 2 here to calculate optimal SNRs. And then we'll use 1, 2, and 3 to compare different EMRIs across the parameter space so that we can understand how changing certain parameters affects our ability to measure sources and to kind of see what areas of the parameter space that we actually have access to, things like that. Is there any questions before I switch over to the notebook? Okay, doesn't seem like it, so I'll go ahead and switch over now. Let's see here. Give me 1 second. All right. You should be able to see the notebook now. Let me know if that's not the case. So once again, this notebook was mainly put together by Alvin Chua. I helped in a bit of it, but this is something these are topics that we discuss a lot and have worked on a lot together. So I just want to make sure that he's kind of credited as well here. So it has installation instructions at the top as well. These are the same ones I posted in the Slack. So if you end up doing this offline later or something, these are the install instructions that you have to follow. If you have any problems with installation, please reach out to myself or Alvin, and we can work them out and figure them out. As I said in the Slack, we've run into a few issues with Python 2. I can't stress enough that I feel like everyone should be moving to Python 3 by now. But if you have issues installing with Python 2 or any installation issues, please let us know. So I'm just going to kind of go through here a little bit slowly. There's a few blank boxes with the goal of having you all kind of try the calculations before we show you how to do them. If we were in person, I would kind of give you more time for those, but since I can't walk around and help and see how everyone's doing, I'll probably kind of just go slowly through them. So try to do them on your own or try to do them offline. Either way,
Sorry, there's just a request in the chat. Could you make the text a little bit bigger?
Yeah. Is that better?
Yeah, I think so.
Okay. Okay. So hopefully that'll be okay. It should be fine. But so we'll start. You can basically, especially for the start of the notebook, you can just run cells going down. Some of the cells I'm not going to run just because of how long they take to run. And that's generally when we're creating waveforms. So just keep that in mind. I might kind of gloss over those a little bit more quickly. So first we'll start by talking about the Lisa noise curve. So what we're going to present is an analytic fit to the Lisa noise curve. We have the archive number there if you're interested in looking at this more. But when we get a noise curve, we generally talk about it in terms of the power spectral density. It's a description of the stochastic process that is the noise, and it's given in units of 1/Hz. Ultimately, the kind of only added thing we want to show here is the confusion background noise. Let's see. Okay, so I see a question there. So I see you said sorry off topic, no problem. So the sampling rate so first of all, the sampling rate generally will be determined by the kind of experimentalists, the people building the satellite. It will determine what sampling rate we actually get from the satellite. When we do our analyses in terms of data analysis, say practice or something like that, we generally use sampling rates of about 0.1 Hertz, or so, you know, a sample every 10 seconds or a sample every 15 seconds. So the current Lisa Data Challenges data set is sampled every 15 seconds. Now the actual satellite data stream will probably be more on the order of every 1 second or so, but that is not fully decided yet. So back to the noise curve. So one thing we just quickly want to mention is the galactic foreground noise. So it's shown here. So the Lisa noise curve with no foreground noise is shown in blue. But because of the large number of galactic binaries that will be unresolved in LISA, it will create a foreground noise that's kind of represented by this bump down here. But as we analyze longer, this bump will go down because we'll be able to remove more and more binaries from this confusion, and we'll be able to separate them out. So for that reason, for the rest of this tutorial, we'll use the 4-year estimate, which is the nominal mission lifetime. So when we get the data on the back end, this is what what we kind of expect this background noise to look like. In terms of looking at other sources, this can be quite important, especially massive black holes, as well as EMRIs that are at lower frequencies. So to do this, you can just run this cell. This one's pretty quick, so it should just pop out right there. And you can play around with this all you want, but this is the main function here, LISA noise. So if you do this without the duration parameter, it will just give you 4 years. So this is the type of function that we'll be using later on effectively. So now we'll generate some AAK waveforms. So what we have done here is we have simplified the actual interface to the waveform so that we are focusing on the intrinsic parameters plus the distance. And we do this because later in the tutorial, you'll see that we want to look at each of those parameters specifically. The actual AAK waveform lets you put in other things like the sky location and the orientation of the EMRI, different things like that. But for the tutorial, we wanted to simplify it. So those are the inputs that we'll be using today. This is the small mass mu, large mass m, spin, initial separation or semi-mass rectum, eccentricity, inclination, and distance. So I will say, as Alvin notes here in the notes here, is that we will be using detector frame quantities. So this means that if you want to look at an EMRI that you know the source frame parameters, you will have to redshift them to the detector frame as input to the AAK waveform. So ultimately what this waveform generator does is it produces 3 arrays, which is the timestamp, then H plus and H cross. And for the examples that we'll be using, these are hard-coded with 3 million points. These are hard-coded with 3 million points and a sampling rate of 0.1 hertz. So that gives you another answer to the question before. This is kind of a very typical sampling rate that we use. These are hard-coded for the tutorial, not hard-coded in the overall AAK waveform. You can adjust these as you want. So I see another question here. How is the function LISA noise computing the noise? Well, it's just using effectively the analytic fit to the noise from this paper. So if you want to look that up, you can. But basically what it does is you just input frequencies and it uses the formula given in this paper to generate that noise curve. I hope that answers the question, but if not, ask somebody else or we can talk offline either way. So generating an AAK waveform, you guys can all run this cell if you would like while I talk. I've already run it. So this will be the first waveform that we are generating. And so as you can see, we're doing with a total mass or a large mass of 1 million solar masses, a small mass of 10 solar masses, so a mass ratio of 10 to the 5, and these other parameters shown here. And kind of as I alluded to before, we're dealing with a year-long waveform sampled at 0.1 hertz, so 3 million points. And this still takes 23 to 24 seconds or so to do. That's on my laptop, but that's pretty similar to most other more modern laptops and computing cluster nodes. So as you can see, this is really not a timing that is at the level that we need it to be in order to accomplish the data analysis tasks that we want to. So this is the amount of time that it actually takes to generate these waveforms. As Alvin notes here, there are faster versions of the AAK. Like I said, we have a GPU version of the AAK, which would take about 30 milliseconds to generate this waveform. We also have AAK in the frequency domain built for what's called the TDIs in LISA. That function is faster, but it's a bit more finicky. So if you want to use it and you try to use it, let us know if you have any problems. But those are kind of other options you have if you want to run faster waveforms or potentially in a different way with hardware or in the frequency domain. So if we now plot this waveform, we can see what that looks like for the strain over time for H plus and H cross. That's just for the first hour of observing. So once again, we will observe these for years, for a year or more than 1 year. So you can imagine how many cycles we're actually going to get here. And we'll look at the whole waveform here. As we can see, it plunges after about 322 days. And that is, as Alvin notes, partly why we've chosen these parameters. It's so we can calculate the SNR for an effective year-long waveform. Does anyone have any questions about that before we get into the actual SNR calculations? Okay. So to calculate the SNR, we'll need the fast Fourier transform, which is something NumPy provides. That's, as Alvin notes here, this is the type of transform we'll be using. And you'll need these sampling parameters that in the analysis to do it properly. Now, ultimately, we left this box here for you all to try to do it on your own. I'll kind of talk through this while I'll letting you all try to do it a little bit, but then I'll kind of put the answer in here. And later on down here, we have a function for you to do it, so we make sure we do it properly. But when taking Fourier transforms, we have to be very careful, especially in terms of the discrete Fourier transform. So the first thing we have to worry about is that data analysis algorithms generally use the unnormalized transform. This is the default in NumPy and FFTW, but as far as I understand, not the default in Mathematica. So you have to be careful about the normalization done with these FFTs when you're doing the signal-to-noise ratio. Additionally, you have to be careful with the output. We're doing a real fast Fourier transform, so we'll have an output that is has this length shown here with just positive frequency components. Other libraries might not do that, so be careful about the kind of output length of the vectors that based on what you input. So that's something just to look out for. Finally, I would say the most important, and as Alvin mentions, the most overlooked thing is dimensions. So when we do a real Fourier transform, we take a dimensionless time series, Fourier transform it, and then it has units of time. But the DFT remains dimensionless. So when we do a discrete Fourier transform on a dimensionless time domain data set, its transform is dimensionless. So it has different dimensions than a full Fourier transform. And when you're analyzing the signal-to-noise ratio, you really have to be careful about these. So ultimately, we have to add units of dt or so. So I'll now kind of post my very quick version of this, my correct way of quickly writing this up to do it. So this is kind of how I like to do this and how I wrote it up. So we run this, and we can see that the waveform that we're looking at with these parameters, is about 22. So this means it's detectable. Depending on the algorithm you use for detection, that threshold of detectable SNR can change. But ultimately, this is what we see. So for the rest of the time, we'll be using things like this shown here. Alvin has put together these functions so that we can use them and run them and make sure we have the actual calculations correct. So as I said, it's about 15 to 20. And one thing we'll do here now is we'll visualize the SNR using the characteristic strain plots that we looked at a little bit in the slides there. So once again, this is just a way of kind of integrating by eye what the SNR is on a log-log plot. But once again, this is just really more qualitative, but can allow you to really compare things and understand what's going on. So if we kind of set that up here, we'll declare the characteristic strain function, and we will generate it here. So as we can see, this is one of the ones we looked at in the PowerPoint. And what we can see here is that this area in the center. Okay, I see someone said they got an error that DT's. That means you did not run this cell. So make sure you run this cell that gets all these quantities going. Yeah, DT equals 10 right there. If we keep looking at this, if we look at this area of the sensitivity curve, we can tell that there is a decent chunk of area between the signal and the noise curve. This is where our signal to noise ratio is generated. Obviously, these parts out here will not have much an effect in terms of what we can measure. So now with the SNR in hand and the characteristic strain in hand, we'll kind of walk through changing the parameters to kind of see what this does in terms of the signal to noise ratio. So this is the kind of thing that as a data analyst, this is something we care about when we're talking about different areas of the parameter space. Okay, I see a longer question here. I'll get to that at the end. I see another question. Should you use a window on the time series? So this is something that Alvin and I talk a lot about. There is some very nuanced details, I think, in terms of answer that question. Just because, like, for example, massive black holes, we generally do our practice analyses in the frequency domain, but we'll eventually have to do in the time domain. So it's not exactly clear exactly how we're going to do the windowing and different things like that. Hopefully we can just run our analyses almost entirely in the time domain and not have to worry about it. So just something to keep in mind, I guess. But I would say that's not something that we do a lot, is specific windowing and data analysis. But it's something that we are really thinking about. So the tails themselves, probably, no, they're not physical. They are, remnants of the Fourier transform, the discrete Fourier transform. But ultimately, because the discrete Fourier transform is, an exact representation of the time domain signal in the frequency domain, in its window, I guess, it's still kind of just as valid because we need these tails to transform it back into the time domain in the exact waveform that we, gave it originally. So that's why I think it's a bit more of a nuanced conversation. So there's another good question here of whether or not it returns plus and cross polarizations or the 1 and 2 channel responses. I believe I actually have to ask Alvin for this specific notebook implementation, but I believe it is returning H plus and H cross, which means that when you are using the AAK offline, ultimately, what you'll want to do if you want the actual response functions is you'll want to turn, it's got a parameter in there called Lisa. So Lisa has to be set to true. But I believe for this, we're just looking at H plus and H cross, not the response as seen by the detector. So the initial separation, that's the first parameter we're going to look at. We're going to use all the same parameters that we did before, but now we're going to set the separation to longer. So you guys can run this while I kind of talk if you'd like. You can see it took slightly more time because it takes a bit longer to plunge. And we can see that if we zoom in on the first hour, there is slightly fewer cycles than what we saw before, as expected at larger separations. But the main thing we want to concentrate on here is calculating the SNR. So as you can see in mine, and hopefully eventually in yours, you'll see that the signal to noise ratio for this source is just above 2. So this source is not detectable. Now, we can also visualize this in terms of the characteristic strain, as will come up here momentarily. So this is the plot that I showed on the PowerPoint. You can see that the red has much less area between it and the sensitivity curve. This is why we see a lower signal to noise ratio than the green. This is, once again, how we can use the characteristic strain is to kind of visually understand the differences here. Also, this has kind of more things going on at lower frequencies, which we would expect since we are kind of backing up this initial starting position to larger separations. So that's something that the larger separations do. It kind of pulls us out of the realm of detectability, depending on the source that you're looking at, depending on the masses and the mass ratio and things like that. But as Alvin notes here, this signal, I don't think it plunges actually in the full time. So if we detect this for longer than a year, it will most likely become a detectable source. But in the version that we're looking at right now, it's not detectable in terms of its year-long waveform. So the next thing we'll look at is initial eccentricity. So here we will up the eccentricity from 0.1 to 0.4. And as we'll see, I'm not going to run it. I already ran it, but if you want to run it, you can. This waveform takes about 3 times longer. That's because the AAK model relies heavily on the decomposition into harmonic modes. So at higher eccentricity, we need more modes to contribute to the waveform, therefore causing it to take a longer amount of time. Even with that said, the plunge is generally similar. We still see it plunging at about 306 days. So it's effectively a year-long waveform. If we look at, once again, the first hour, we can now see these more eccentric modulations that we expect to see. And then we also want to look at the signal-to-noise ratio. So as you can see here, as calculated on mine, you can see the signal-to-noise ratio is about 20. Now, this might be surprising to some, the fact that it doesn't have a large effect, but we can once again kind of visualize this in the characteristic strain plot. So ultimately, as you'll see it pop up, they overlap pretty heavily now, but there is kind of areas in here where there's less area between the sensitivity curve compared to waveform 1, but it's kind of spread out over more frequencies. So the frequency band is larger, but it's kind of proximity to the noise curve varies a lot more and can be in many locations closer to the sensitivity curve than the green waveform where it kind of consistently stays above it. So that's why we can see it kind of doesn't have a whole lot of effect on the overall SNR when we adjust the eccentricity. Now here we'll look at the mass ratio. Once again, you can generate it on your own. This one's actually very fast. It takes just over 3 seconds. And the question is why? Why did this signal plunge much sooner? We have now increased the secondary mass to 10 to the 2, which means our mass ratio is now only 10 to the 4. And the difference can be seen by just looking at the radiation reaction timescale, as I'm sure you all are familiar with. So ultimately, we actually have to adjust this signal in order to look at a year-long waveform. So to do that, you can do that on your own. I'm just going to kind of keep going so that we can get through as much of this as possible. But if you increase the initial separation to 13.3, which it says down here, you will actually see this waveform now plunging at about 325 days, allowing us to look more at a realistic 1-year waveform than if we just looked here. So ultimately, we once again also want to find the SNR of this source. It's 83, so it is about a factor of 4 times higher. And the reason for this is that the amplitude of the signal is boosted by the secondary mass. So one thing that can really affect the amplitude of the signal is the mass of the secondary. So at very small masses in the secondary, you'll get low amplitude. And as that goes up, you'll get higher amplitude. But also the larger separation allows us to operate at lower frequencies for a portion of this, which means a better sensitivity in terms of the Lisa noise curve. And you can see that in this plot here. So we can see that this is higher up. The amplitudes are higher because the secondary has a larger mass. And the kind of spread of the frequencies is a bit larger because we're starting at a larger separation and kind of going all the further across the band. And you can see very clearly here, why the signal-to-noise ratio is that factor higher. So this is once again a very good example of where the characteristic strain plot can really illuminate differences in the plot. So here, especially if we were in person, I would pose the question, will a similar EMRI with a secondary of 1 solar mass be detectable in the last year before plunge? The answer is no, it will not. Because the secondary of 1 solar mass will lower the amplitude so much that it will go below the sensitivity curve. And if you want to do this, in your spare time, feel free to run this EMRI with that solar mass. You'll see this characteristic strain curve drop much further down here to a non-detectable SNR level. So now here we'll look at the total mass. So once again, same parameters as waveform 1, but we've now changed the total mass. So the mass ratio is now the same as waveform 1. We have a mass ratio of 10 to the 5, but we now have a total mass, or a larger mass of 100,000 solar masses instead of 1 million. This, once again, is a fast waveform because it plunges quickly. So the question is, why is the plunge of this waveform just as quick as the plunge of the waveform we looked at up here, which had a different mass ratio? Once again, the answer is the radiation reaction timescale. It's actually equivalent to waveform 4, which we just looked at, which is why it plunges on a similar timescale. So once again, we'll have to adjust this one to make it plunge in closer to a year, which we can do by setting a separation of about 5.6 m. So I have already done that. You can do that, in your free time if you want to after. So we now see a close to a year-long waveform and an SNR of 5. So once again, we would expect this to be low for two main reasons. One, we're starting at an even lower frequency, or starting at a lower than the overall, because the primary is larger than waveform 1. But the amplitude of the signal is again decreased by the smaller secondary mass. So the secondary mass is really, I think, the key component to this, decreasing the amplitude here to lower values. As you can see here, sorry, I forgot to mention, we do change this to 10 to the 7 solar masses here after we kind of look at this. Sorry, I glossed over that. That's why we have a larger primary mass. That's why we deal at lower frequencies. But the separation of 8M was actually too large. Sorry for the confusion. So we actually had to decrease that to a separation of 5.6 to get a year-long waveform. So that's what we're looking at here. Once again, we can look at the strain plot. We can see that for this waveform with a very large primary mass, it evolves at very low frequencies, and therefore, is in an area of the sensitivity curve where we have larger noise, which results in the lower signal-to-noise ratio that we end up seeing. Now, I think I'm coming up here right on the time. If you don't mind, this is the last box, so I'll just get through this and I'll answer any other questions. So last thing we want to look at, which I think is an interesting one, is the primary spin. If we generate another waveform, so similar to waveform 1, but we now do a spin with a Schwarzschild injection and then a spin of 0.9, we do change the P parameter because of the differences in where they plunge in terms of their distance away from the central MBH. So we just want to look at the SNR of these sources, and we see that it's 14 for a Schwarzschild injection and 27 for a 0.9 spin injection for the Kerr version. And ultimately, we want to ask the question, does the SNR vary strongly with the spin of the primary? The answer is no, it does not. The reason we see the increase in the SNR is not a direct effect of the spin. It's actually an indirect effect of the spin. Since we add the spin, it means that the secondary can actually get closer to the primary before it plunges. And when it's closer into the primary, it has a larger gravitational wave amplitude, which results in this larger signal-to-noise ratio. So it's an indirect effect actually of the spin rather than a direct effect. So that's the whole tutorial. I know I went through kind of quickly. Feel free to email us, ask us questions offline, or in the Slack or anything like that. We'll be happy to walk through this, but I hope you gained a sense of how we look at SNRs, how we look at these things from a data analysis standpoint, and how different parameters adjust the SNRs accordingly, as well as how to kind of use these characteristic strain plots to give a qualitative assessment of how that works. So I'll end there and I'll answer, I guess. So I have one question here and I'll go back to the longer question from before. How is determined the boundary between the in-spiral and the plunge phases? So that is generally a better question for Alvin. I'm sorry, that's not exactly in my wheelhouse to answer. I know that the numerical kludge has I think a better version of the plunge. I don't know exactly what it does, but I think it's kind of a more kind of mathematical way of doing it. Whereas the AAK itself has a pretty kind of ad hoc plunge that I know Alvin doesn't really like, but it's part of it. So that's like I said, it's probably a better question for Alvin, but I'm not exactly sure. We can probably talk offline. I've looked at this in the code. There is a boundary that determines that separation, but I'm not exactly sure off the top of my head what it is. So I'm scrolling up here back to the longer question. So I see the longer question about, I think the kind of the Cluj model fidelity in comparison to real EMRI waveforms. So I will readily admit that my EMRI expertise is more on the computational and analysis side, and not on the very specific orbital calculations that most of you all work on. But my understanding is that to really look at systematic errors, to look at in terms of a more extensive study, you need to have long waveforms. My understanding is that that's pretty hard to do at scale for any of the models that we have so far. Yeah, so yeah, Niels added in here, yeah. So there isn't a good handle, I would say. That was effectively where I was getting. I think ultimately, we do not plan to use the Cluj models in our analysis. That's why I kind of briefly mentioned the waveform that Niels and Alvin and I are working on. But yeah, we don't expect them to be accurate enough to do a vast majority of the analysis that we want to do in the end. Maybe some very basic things, but that's about it. Yeah, that's a good comment from Niels. I agree with the comment. The new waveforms will be as long as you want them to be. It can handle waveforms up to any arbitrary length, really. We've already tested it on waveforms that are year-long waveforms, and we can, yeah, so that's about the approximate timing. I would say we can even go a little bit less than that now that we've fine-tuned a little bit, but that's a pretty safe bet for what it will take in terms of generating a waveform that's a year long. Yeah. Yeah, so the waveform we're working on is restricted to the Schwarzschild geometry with restrictions on the initial eccentricity, but I think pretty lax restrictions overall in terms of generating year-long waveforms with plunge. And we're currently working in the adiabatic regime. Yeah, there you go. But we're putting together a framework that is extensible to Kerr and extensible to further developments of the self-force and things like that. And you'll over the next month or so, you'll see more about this. And I think we're planning to talk about it at Capra as well. So just keep an eye out for that if you're interested in this kind of thing. Yeah.
Okay, I think that's one more question just arrived.
Sorry, when you say your new GPU implementation, do you mean the AAK or the actual fast EMRI waveforms that Niels and I have quickly mentioned? Well, I guess I can say both of them. So the new EMRI waveforms, when we say 200 milliseconds, that is with a GPU. So the fact is, as you all know, we have to deal with many modes, and determining and kind of accurately summing all of these modes is not an easy task, especially for a CPU. It's something that is very well suited to a GPU. So we generally plan to use the GPU in terms of actually using these calculations on the order of 100 milliseconds or so. We will have a CPU version, but we have not tested that to understand how long it will take yet. We've been kind of mainly focusing on the GPU version because we want to make sure we have something fast enough to potentially use for data analysis. So I think that's kind of the general answer. So that 200 milliseconds is actually the GPU implementation. Okay. Well, okay. No other questions. Yeah. Thanks, everyone. Much appreciated.
Yep. I think that is the last question. And so thanks again to Michael and to all the people who presented today. That brings us to the end of the day. Tomorrow we have the final day of the program. The workshop is going to be devoted to development of the toolkit. So anyone who's interested in contributing to the toolkit or learning how the toolkit is developed or adding any aspects to the toolkit is welcome to join. And that will be starting at 12 noon tomorrow.
just wanted to add one thing. I try to keep all the materials on the website up to date, so you can go and review the talks on YouTube right away and see the materials there if you are still thirsty to understand everything that was said today. Okay.